Welcome to the course, where we will build the solid foundation you need to master the AX0-100 certification and excel as a network video professional. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to Axis Communications in any way. All trademarks belong to their respective owners. In this introductory module, we explore the core domains of Axis network video technology to prepare you for the certification journey ahead. We will cover the exam structure and the essential technical pillars that define modern security system design. Achieving the Axis Network Video certification is a significant milestone that validates your proficiency in designing and deploying complex surveillance systems. This course is purpose-built to distill years of engineering best practices into actionable knowledge that you can apply immediately to real-world infrastructure. You will learn to navigate the intricacies of camera optics, network configuration, and strategic system design with professional confidence. By focusing on the underlying engineering principles, we ensure that you are not just memorizing exam answers, but truly understanding how modern security solutions function in a networked ecosystem. The AX0-100 exam evaluates your grasp of 6 critical domains that every modern security engineer must master for reliable system deployment. We begin with system design and camera placement, where you learn to translate physical space requirements into technical specifications. You will progress through camera technology, learning how sensor dynamics and lighting conditions influence the capture of high-quality video. The curriculum then moves into network technologies, ensuring you understand the protocols and power delivery methods that sustain a robust video infrastructure. We further analyze video compression standards like H264 and H265, alongside sophisticated storage strategies to manage bandwidth efficiently. Finally, we address installation management and system maintenance to ensure long-term reliability and cybersecurity compliance in every deployment. Transitioning into the world of professional network video requires a disciplined approach to both your studies and your field methodology. Success in this field relies on an analytical mindset where you balance technical constraints against the specific operational needs of the customer. We will spend time discussing how to leverage Axis documentation effectively, turning these resources into your primary technical compass. Understanding the exam format is, of course, a practical necessity to pace your progress. But our deeper goal is to help you internalize the methodology Axis expects of its certified professionals. When you finish this course, you will possess a structured framework that turns abstract security requirements into validated, high-performance system designs. As we move forward together, keep in mind that these technical concepts form a tightly interconnected graph where every choice impacts system health. A decision in camera placement dictates the necessary focal length, which in turn influences the compression requirements and available network bandwidth. By mastering these components individually and understanding their collective behavior, you reduce technical debt before a single piece of hardware is mounted. We are here to ensure you approach each topic with the precision required for high-stakes environments. Professional certification is an investment in your career trajectory, proving that you have met the rigorous standards required by the current industry landscape. I look forward to guiding you through these technical modules in the next lecture. Welcome to the first lesson of our chapter on system design. In this module, we will explore the core principles of effective camera placement to ensure your surveillance infrastructure meets its security objectives. Building a robust video security solution is rarely about simply mounting cameras wherever a wall happens to exist. Instead, we must treat camera placement as a rigorous engineering exercise, where the goal is to maximize optical utility while acknowledging physical and environmental constraints. When we evaluate an environment, we need to consider the interplay between mounting height, the angle of view, and the specific security requirement of the zone in question. A camera placed too high might provide a great overview of a parking lot, but it may fail to capture the critical facial details necessary for identification at an entry point. Conversely, a low-mounted camera might capture perfect identification footage, but become susceptible to vandalism or obstruction by passing crowds. We always aim for a balance where the physical position of the hardware inherently supports the operational intent of the surveillance project. One of the most persistent challenges we face is the existence of physical obstructions that degrade the utility of our sensors. When surveying a site, you must proactively identify pillars, foliage, HVAC ducting, and temporary storage racks that may interfere with the intended field of view. It is not sufficient to look at a floor plan on a screen, as architectural drawings often omit non-permanent fixtures that end up blocking critical views. A camera that functions perfectly during a site survey might find itself staring at a newly installed display case or a growing hedge 6 months later. Whenever possible, we account for these fluctuations by verifying the line of sight during the planning phase and selecting positions that offer a buffer against foreseeable environmental changes. If a location is crowded with dynamic objects, we should consider alternative mounting topologies like overhead pendants or wall extender brackets. Lighting conditions dictate the success of any camera placement strategy, particularly when dealing with natural light. We constantly battle the physics of high contrast scenes where a camera faces a bright doorway or a high glare window, potentially washing out the entire image. While modern hardware handles high dynamic range effectively, it is always superior to place the camera in a position where it is not looking directly into the strongest light source. If you have no choice but to point a camera toward an exterior entrance, consider how the mounting angle might minimize the impact of the sun at different times of the year. Glare from artificial lights can also create internal reflections within the lens, which leads to ghosting or blurring of the primary subject. By slightly adjusting the pan or tilt of the mount, we can often steer the optical path away from these offending light sources without sacrificing the coverage area. When we shift our focus to choke points and egress points, our strategy must evolve from wide area observation to specific, actionable data collection. Entryways and hallways act as natural funnels where people are constrained to move through a predictable space, allowing us to deploy lenses with specific focal lengths tuned for better identification. Perimeter surveillance is fundamentally different, as the priority here often involves identifying intrusions over vast areas rather than capturing forensic-grade facial features. We align our cameras to monitor these borders using wide angles, accepting that pixel density will drop significantly compared to our choke point assets. Understanding this distinction allows us to design a security posture that is layered rather than uniform. A well-designed system allocates resources precisely where they are needed, maintaining efficiency across the entire network architecture. Finally, we must consider the aesthetic requirements of the facility without compromising the integrity of security. Many commercial environments rely on architectural consistency, meaning that large, conspicuous housing units are often viewed as undesirable by facility managers or interior designers. Axis provides various form factors designed to blend into these environments, but technical performance must always remain the primary decision criterion. If a discrete camera cannot achieve the necessary resolution or angle of view, then an aesthetic objection must be countered with a clear explanation of the potential security gap. Ultimately, you are tasked with protecting assets and people, and the physical placement of your hardware is the foundation upon which that security mandate rests. Follow these guidelines for every deployment, and you will ensure your system operates at its maximum potential. I look forward to discussing how we measure this efficiency in the next session. Welcome back to our discussion on system design and camera placement. In this lesson, we will examine pixel density and how it functions as the primary determinant for the level of detail we can extract from a surveillance scene. When we talk about image quality in the context of network video, we are essentially talking about the distribution of information across a sensor. Pixel density, often expressed as pixels per meter or pixels per foot, serves as a quantitative bridge between a physical scene and a digital image. If you consider an object moving through a field of view, the camera must capture enough samples of that object to make it recognizable by a human operator or a machine learning algorithm. We calculate this by taking the horizontal or vertical resolution and dividing it by the physical dimensions of the area being covered. If your goal is to identify a person, the standard recommendation often points towards specific pixel counts across the target area to ensure that the facial features are rendered with enough clarity. It is not sufficient to simply have a high-resolution sensor. The lens focal length must also focus those pixels precisely where they are needed most. Failure to perform this calculation leads to scenarios where a camera records vast amounts of motion, yet the footage rendered is essentially a blurred mess of pixels that lacks forensic utility. To make these calculations deterministic, we must map our desired resolution against the physical capabilities of the sensor and the field of view. Suppose we have a scene where we need to identify license plates at a distance of 20 meters. We know the width of the target area, for example, 4 meters across at that specific distance. If our camera has a horizontal resolution of 1920 pixels, we divide those 1920 pixels by the 4 meters of width. This gives us 480 pixels per meter. This mathematical exercise allows us to verify if our chosen hardware can actually meet the objective before we ever mount it to a wall. If the requirement for license plate recognition dictates a minimum of 250 pixels per meter, our calculated 480 pixels per meter provides a sufficient margin. This approach effectively removes the guesswork and subjective opinions that often plague system design, replacing them with objective, verifiable data points. However, there is always a trade-off when we increase pixel density, as we are essentially concentrating limited resources into a smaller portion of the entire scene. Higher pixel density requires more data, which leads us directly into a conversation about bandwidth and storage utilization overhead. If you increase the focal length to achieve better detail on a specific target, you narrow the field of view, potentially missing context that might be necessary for broader situational awareness. Conversely, installing a wide-angle lens to cover a larger area drastically lowers the pixel density, rendering the background imagery practically useless for fine detail extraction. This creates a bottleneck because a system with insufficient pixels per meter will always suffer from poor image utility, regardless of the compression algorithm used later. You cannot retrieve information that was never captured by the sensor in the first place, regardless of how much processing power you throw at the resulting video files. We must look at this from the perspective of forensic investigators who rely on these files during post-incident analysis. If they have to zoom into a grainy, low-density image, they are relying on interpolation, which introduces noise rather than clarity. Therefore, our design phase must focus on aligning camera specifications with the specific operational constraints of the client. Over-engineering occurs when we specify ultra-high resolution for every single camera in a system without considering the storage costs associated with that high data throughput. Underperformance, on the other hand, is the more catastrophic failure where the system fails to provide evidence when it is needed most. By mastering the relationship between sensor resolution, focal length, and distance, we ensure that the system performs exactly as expected. We are essentially modeling reality within the constraints of digital imaging, ensuring that the technology serves the security outcome rather than dictating it. See you in the next lecture. Welcome back. And today, we shall dive into the DORI Standard, which is fundamental for anyone serious about designing reliable video surveillance systems. If you are aiming to transition from guessing where to place cameras to engineering systems with predictable outcomes, this chapter is the cornerstone of your professional development. We will dissect the DORI framework: detection, observation, recognition, and identification, to turn abstract security requirements into precise, hardware-based specifications that hold up under rigorous scrutiny. Through our curriculum, you will master the pixel density thresholds that govern these 4 levels, ensuring your designs never fall short of client expectations. By learning how to mathematically map these metrics to lens and sensor capabilities, you will gain the ability to justify every single camera placement in your future projects. The DORI standard is essentially a shorthand for defining what a camera needs to see to perform a specific task effectively. It is based on the EN 62676-4 international standard, which dictates the number of pixels per meter or foot required to view a human target with a certain degree of confidence. When we speak of detection, we are looking for at least 25 pixels per meter, which allows an operator to distinguish the presence of a human being against a background. This is purely for awareness, letting someone know that motion or an object of interest has appeared in the scene, without providing any details about what that object is. If your project constraints only require basic perimeter monitoring or simple alarm triggering, this low-resolution threshold is often the primary driver for sensor selection. Moving up the ladder, observation requires 63 pixels per meter, a level that begins to provide some context regarding the activity of the target. At this resolution, an operator can see the characteristic movements of a person and perhaps the nature of their clothing or the surroundings they are interacting with. It is an intermediate step that sits comfortably between basic detection and the more demanding work of recognition. You will find that this level is often sufficient for general area surveillance, where specific identification is not requested by the end user or dictated by forensic legal requirements. Designing for observation is a balancing act, as it requires enough resolution to be useful while respecting the bandwidth and storage limitations that come with higher pixel counts. Recognition brings us to a threshold of 125 pixels per meter, which is arguably the most common requirement for security operations centers that focus on incident management. At this density, the operator can recognize a person or a known object with a high degree of probability, even if the individual's face is not perfectly clear. This is where you begin to link the visual stream to human intuition, allowing an officer to decide whether someone is a threat or merely a visitor. When you are configuring a system, this level is the threshold where you start needing to pay close attention to the focal length and the distance from the subject to the camera. It is a critical milestone in system design because it moves the output from valid raw data into actionable intelligence for your customer. Identification demands the highest standard, requiring 250 pixels per meter to achieve what the industry calls forensic level evidence. This level of detail is necessary to produce an image that can be reliably used in a court of law to verify the identity of a specific person. It is visually demanding and forces the engineer to consider much more than just the sensor's native resolution. You must factor in lens quality, lighting conditions, and the contrast of the target against the background, as these environmental variables can quickly degrade a perfectly calculated theoretical image. If your client explicitly asks for the capability to identify a perpetrator, you are obligated to plan for this level of density, which often necessitates tighter fields of view or proximity placement. It is vital to understand that these thresholds are mathematical ideals that assume a clear, high-contrast environment. In reality, factors such as motion blur, low lighting, or poor sensor sensitivity can effectively drop your performance below your DORI targets even if your pixel count looks correct on paper. For instance, if you have a camera designed for identification but it is mounted in a dark corner without adequate illumination, the noise floor of the sensor might completely obscure the fine detail needed for facial recognition. You must learn to look at the intersection between the lens focal length, the sensor size, and the environmental light levels to ensure your theoretical DORI values translate into real-world results. Proactive calculation, rather than post-installation correction, is the mark of a seasoned security system designer. When we analyze the field of view, we essentially divide the physical width of the target area by the number of pixels available from the camera sensor. If you have a sensor providing 1,920 pixels in width and you need 250 pixels per meter for identification, the maximum width of your scene must be strictly controlled to maintain that density across the entire field. This simple division is why you cannot just use a wide-angle lens for every location and expect to achieve forensic clarity. Every camera in your design should have an assigned DORI requirement, and your job is to select the optics that force the subject to occupy the necessary proportion of the frame. This systematic approach eliminates guesswork and ensures that every dollar the client spends contributes to a functional, high-performance security infrastructure. By adhering to the DORI framework throughout the design process, you shift the conversation from vague performance goals to tangible, validated requirements. This not only builds immense trust with the stakeholders, but also forces you to confront the physical limitations of your hardware early in the budgeting phase. If a specific area requires identification, but the physical distance makes that impossible with the preferred camera technology, you now have the data to explain why a different sensor or a different mounting location is required. Engineering through DORI is the best protection any professional can have against complaints of poor image quality after the project has been signed off. It is about precision, and it is about delivering exactly what the client's security protocol demands. I will see you in the next lesson. Welcome back. Today, we are delving into the geometric foundations of surveillance architecture by exploring field of view mathematics. When we approach the task of camera placement, we are essentially performing a spatial projection exercise. The field of view, or FOV, is not merely a marketing metric but a rigid function of sensor dimensions and the focal length of the objective lens. To calculate horizontal, vertical, or diagonal coverage, we rely on basic trigonometry where the angle represents the field seen by the sensor. If you imagine the camera as the apex of a triangle, the sensor width forms the opposite side, and the focal length dictates the distance along the adjacent axis. By applying the arctangent function to the ratio of the sensor dimension to the focal length, you derive half the angle of the field of view. Doubling this result provides the total angle, allowing you to map the specific geographical area a camera will capture before you even open a mounting bracket. The choice of aspect ratio introduces a significant variable into these calculations that often escapes novice designers. A 4:3 sensor format, for instance, distributes its surface area differently than the modern 16:9 widescreen standard, directly influencing how horizontal sprawl versus vertical depth is prioritized. When you change these ratios, you're effectively cropping or expanding the effective sensor area that light hits, which changes the math for the lenses being used. If you are calculating the coverage for a wide area, transitioning to 16:9 might provide a greater horizontal span, but it simultaneously forces a reduction in vertical height if the focal length remains constant. Engineers must account for these geometry changes to ensure that the resulting image does not suffer from unexpected blind spots. Failing to compute these spatial relationships often leads to gaps in coverage where the physical environment is not adequately monitored by the overlapping FOVs. Precision in your design phase relies on your ability to perform these technical drills regarding object proportions and distances. As the distance from the camera to the target increases, the field of coverage width expands proportionally according to the lens's angular FOV. This relationship is linear, meaning that if you know your field width at 10 meters, you can mathematically predict your field width at 20 meters with absolute certainty. By integrating these trigonometric models into your workflow, you can effectively minimize the total number of cameras required for a given installation. Efficiency in system design is not about having more cameras, but about ensuring that every camera is placed and focused to maximize its utility within the surveillance theater. Understanding these mathematical constraints is the bedrock of creating an uninterrupted visual chain of custody that covers complex, multi-dimensional environments effectively. See you in the next lesson. Welcome back. In this session, we investigate the fundamental relationship between focal length and spatial coverage to refine our approach to lens selection for network video systems. When we talk about focal length, we are fundamentally discussing the distance between the optical center of the lens and the image sensor when the subject is in focus. This measurement, usually expressed in millimeters, dictates the field of view that the camera can capture. A shorter focal length produces a wide angle of view, which is ideal for situational awareness in large, open spaces, while a longer focal length narrows the view, providing the magnification necessary for identifying objects at a distance. It is important to realize that the behavior of the lens is also intrinsically linked to the size of the camera sensor. A lens with a specific focal length will behave differently on a quarter-inch sensor compared to a full-frame sensor, effectively changing the crop factor and the resulting horizontal and vertical field of views. You should view the lens and sensor as a single optical system rather than isolated components. If you disregard the sensor format during your design phase, you will inevitably end up with a field of view that deviates from your initial requirements. This is where many practitioners encounter issues, assuming that focal length alone determines the coverage, forgetting the role of the sensor's physical dimensions. Proper planning requires you to harmonize these properties to ensure the resulting video stream provides the specific coverage needed for your security objectives. Wide-angle lenses, characterized by shorter focal lengths, introduce a unique set of challenges, most notably barrel distortion. This optical phenomenon causes straight lines near the edges of the frame to appear curved or bowing outward, which can complicate the interpretation of spatial geometry in an image. While wide-angle lenses excel at capturing large areas, this distortion is a trade-off that we must account for when designing a system where forensic accuracy is paramount. Conversely, telephoto lenses allow for a more precise, narrow view, which is essential for capturing granular detail at long distances, such as an entry point located across a parking lot. However, this comes at the cost of depth of field compression, where the distance between foreground and background objects appears smaller than it truly is. This compression can sometimes mask the spatial depth needed for tracking a subject moving through a scene, requiring careful consideration during the hardware specification phase. When you select a lens, you are fundamentally making a trade-off between the width of the terrain you monitor and the forensic detail you can extract at a given range. A robust surveillance design balances these competing optical characteristics to ensure that the image utility matches the security requirement for the specific topography. To translate these concepts into a scientifically rigorous plan, we must integrate the DORI Standard, which defines detection, observation, recognition, and identification, with our focal length calculations. Calculating the optimal focal length for a specific scenario typically involves using the known distance to the target, the width of the area of interest, and the sensor's active imaging area width. The formula essentially ratio matches the sensor size to the focal length against the target width and distance, allowing you to specify a lens that hits your coverage requirements exactly. By working backward from your forensic goals, such as the pixel density required for facial recognition at a specific doorway, you remove the guesswork from hardware selection. This shift from reactive hardware choices to proactive engineering ensures that every camera deployed has a purpose and sufficient clarity for its intended site. Neglecting these calculations often leads to over-imaging a space with wide lenses that lack resolution, or conversely, under-imaging with telephoto lenses that miss critical activity occurring just outside the narrow field of view. Mastering this mathematical approach is what separates a generic installation from a professional-grade access network video deployment. See you in the next lecture. Welcome back to our exploration of access network video systems. In this chapter, we will synthesize our previous theoretical foundations to engineer practical, comprehensive, and resilient security architectures. If you are aiming to master the intricacies of surveillance design, this module is your bridge from academic theory to professional-grade implementation. You will learn to articulate specific hardware needs based on complex client requirements rather than generic assumptions. We focus on transforming abstract security vulnerabilities into optimized access architectures that balance strict image quality mandates with the harsh realities of project budgets. By the end of this series, your ability to justify camera selection and placement will distinguish you as a true authority in security engineering. Design begins by acknowledging that surveillance is never a one-size-fits-all endeavor, but a series of interconnected constraints. When we sit down to draft a comprehensive site audit, we cannot simply look at a floor plan in isolation. We must map localized threats to specific hardware capabilities. A camera responsible for perimeter detection requires vastly different optics and sensor logic than one intended for interior identification in a chaotic retail environment. We start by establishing the required pixel density for each critical area, ensuring that our hardware selection supports the necessary DORI metrics. The danger lies in over-provisioning every location, which leads to budget exhaustion, or conversely, under-provisioning, which results in footage that is legally useless in a court of law. The mathematical rigor of field-of-view calculations dictates the physical placement of hardware, but this must be reconciled with the realities of network infrastructure. We must track the bandwidth and storage requirements generated by our chosen resolution and frame rate settings against the throughput limits of the client's existing switches. Often, an optimized design requires us to leverage advanced compression technologies to maintain high-quality streams without flooding the network. We must consider the environmental impact on the hardware as well, such as extreme temperatures or high moisture, which necessitate specific ingress protection ratings. These design choices are not arbitrary. They are the result of calculated trade-offs where we sacrifice secondary coverage to ensure total clarity on primary assets. A robust blueprint specifies everything from the exact camera model to the mounting hardware and optical configurations required for the job. You should think of these designs as a language that communicates your technical expertise to stakeholders who might not understand the underlying physics. If you cannot justify why a specific focal length was selected for a site, you will fail to maintain operational coherence when conditions inevitably change. We look for synergy between the camera's sensor dynamics and the lighting conditions of the scene, ensuring that every pixel contributes to the detection rate. It is this level of detail that separates a drawing of a camera on a map from a functional, reliable security framework that will survive years of use. Consider the scenario of a large warehouse loading dock, which presents a high-contrast environment with significant movement throughout the day. We need to decide if we are prioritizing the identification of faces or the detection of vehicle license plates, as the pixel density requirements for these tasks are fundamentally different. A wide-angle field of view satisfies general awareness, but it fails to provide the forensic detail needed for actionable incidents, forcing us to consider multi-sensor or high-resolution solutions. We then evaluate the storage impact of these choices, perhaps incorporating edge storage to offload traffic from the primary network during peak hours. This holistic perspective ensures that the technical blueprint is economically viable while remaining superior in its operational output. Finally, we must consider the human element of hardware maintenance and physical security against sabotage. A camera is only useful if it remains operational, so our designs account for the physical mounting height and the likelihood of intentional tampering. We select our cabling and enclosures to minimize exposure to elements and malicious actors, turning the camera into a hardened node on the network. Every connection must be documented, and every configuration choice must be validated against the client's original security mandates. When the design is finished, it should be a cohesive document where every piece of equipment has a justified purpose and every technical parameter is calibrated to optimize performance. See you in the next lecture. Welcome back. Today we examine the intricate mechanics of image sensors, which serve as the foundation for every visual data point captured in a network video system. To understand modern surveillance, one must first look at the complementary metal oxide semiconductor, or CMOS, sensor. Unlike older charge-coupled device technology, CMOS sensors allow for high integration, where the conversion from light to digital signal occurs right at the pixel level. This architecture is fundamental to access cameras because it enables lower power consumption and higher readout speeds, which are critical for high-resolution video streams. When we talk about light-gathering capabilities, we are essentially discussing the ability of the individual photodiodes to collect photons and convert them into electrical charges. Quantum efficiency becomes our primary metric here, representing the ratio of electrons generated to the number of incident photons striking the sensor surface. A high quantum efficiency rating means the sensor is exceptionally sensitive to light, allowing for clearer images in environments where traditional cameras would produce only noise. The physical dimensions of these pixels are just as critical as the number of total pixels on an array. As manufacturers attempt to push higher resolutions, the physical area of individual pixels often decreases, placing a constraint on the amount of light each photodiode can capture. This trade-off is a classic engineering dilemma, where moving toward a higher pixel count can paradoxically result in worse performance in dim lighting. Larger pixels typically exhibit better signal-to-noise ratios, providing a cleaner feed because they generate a stronger raw signal that outweighs the inherent thermal noise of the electronics. When you are specifying a camera for a low-light environment, the physical size of the sensor format becomes a dominant factor in your design. A larger sensor with bigger pixels will almost always outperform a smaller sensor with an equivalent or higher resolution when light levels drop below the threshold of human capability. Moving into the realm of temporal mechanics, we must distinguish between rolling and global shutters, as this choice dictates how a sensor captures reality. Most modern security cameras use a rolling shutter, which records the image by scanning across the sensor line by line, rather than capturing the entire frame simultaneously. This method is efficient and cost-effective, yet it introduces the risk of geometric distortion if the subject moves faster than the readout speed. We call this phenomenon the jello effect, or skew, where rapidly moving objects appear slanted or warped because the top of the object was captured at a different time than the bottom. In high-speed surveillance scenarios, such as capturing license plates on a highway, this distortion can invalidate forensic evidence entirely. Understanding the sensor readout cycle allows a designer to determine if a specific camera model is capable of freezing motion without introducing these artifacts into the final evidence chain. Sensor noise profiles are the final variable in this complex equation of image quality. Every electronic circuit generates heat, and that heat contributes to background noise that can obscure details in a dark scene. Through sophisticated signal-to-noise ratio optimization, digital sensors attempt to filter out this thermal interference without sacrificing critical scene information. Engineers have created algorithms that balance the need for image sharpening with the necessity of suppressing graininess, but no algorithm can fix a signal that is entirely overwhelmed by noise. Your goal as a designer is to match the sensor characteristics to the scene volatility, ensuring that each photodiode receives enough light to maintain a robust signal. By focusing on these hardware fundamentals rather than just marketing specifications like megapixels, you gain a significant advantage in delivering a system that yields usable, actionable intelligence under any lighting condition. See you in the next lecture. Hello. Today we are looking at the distinction between varifocal and fixed lenses, specifically how their internal mechanics dictate their application in professional surveillance environments. When engineers select a lens for a camera deployment, the most fundamental decision revolves around whether the field of view needs to be adjustable post-installation. A fixed focal length lens is engineered with a proprietary configuration of glass elements that cannot move relative to one another to alter the magnification. Because there are no moving parts required to adjust the zoom, the optical path remains highly stable and often allows for a wider aperture, which is beneficial in low-light scenarios. These lenses are most appropriate when the installation environment is well understood, or the camera's location provides a static view that does not require compromise for the sake of flexibility. An Axis camera equipped with a fixed lens provides a predictable and robust optical solution that minimizes the mechanical points of failure within the camera housing. Reliability is the primary advantage here, as the simplicity of the design results in fewer components that could potentially drift or require recalibration due to thermal expansion or vibration. Varifocal lenses occupy the opposite end of the spectrum, offering a complex mechanical assembly that allows the camera operator or installer to adjust the zoom and focus manually or, in newer models, remotely. This architecture consists of multiple lens elements that slide along an internal carriage to change the focal length, which effectively shifts the field of view without physically relocating the camera. This flexibility is invaluable during the installation process, particularly when site constraints prevent a precise, calculated placement beforehand. However, this mechanical complexity introduces susceptibility to optical aberrations if the alignment of the glass elements is not held to extremely tight manufacturing tolerances. The process of adjusting these focal arrays requires careful calibration to ensure that the image remains sharp across the entire zoom range. While early varifocal designs required a manual twist of the lens barrel at the top of a ladder, modern Axis units often utilize remote zoom and focus, significantly reducing the labor involved in commissioning the system. The trade-off between these two technologies is not merely a matter of convenience. It is a question of optical physics and cost management. Fixed lenses generally offer superior light transmission simply because they contain fewer elements, which means there are fewer interfaces where light can be reflected or absorbed. Conversely, the increased number of elements in a varifocal lens creates a more complex path for light, which occasionally results in a smaller maximum aperture, potentially limiting the camera's sensitivity in deep darkness. When an engineer specifies a camera for a standard, static hallway, a fixed lens is an elegant and cost-effective choice that eliminates the variables associated with moving parts. In contrast, securing a large perimeter where the exact required crop of the frame might not be clear until the device is powered on justifies the extra investment in a varifocal system. By matching the mechanical capabilities of the hardware to the specific environmental requirements, we avoid overspending on features we do not need while ensuring the optics do not become the bottleneck for image quality. Depth of field is another critical factor that behaves differently depending on the chosen lens architecture. A fixed lens, particularly one with a shorter focal length, inherently provides a deeper field of focus where objects both near and far remain sharp simultaneously. With a varifocal lens, adjusting the zoom changes the focal length, which in turn compresses the image and alters the depth of field, often making it more sensitive to focus errors. Engineers must pay close attention to the calibration procedure after moving the zoom, especially when deploying focus-assisted tools that utilize contrast detection to find the optimal sharpness point. While modern Axis devices manage these focus motor transitions automatically, understanding the underlying mechanical movement helps diagnose issues where the image might appear soft at the edges or exhibit ghosting. By treating optical setup as a process of balancing light gathering, geometric precision, and coverage requirements, We build networks that are functionally sound and maintain their integrity over long operational cycles. See you in the next lecture. Welcome to this module, where we will examine the intricacies of light regulation in modern network cameras by focusing on advanced iris control mechanisms. In this chapter, we will dissect the mechanical and algorithmic evolution from traditional DC iris systems to the precision of P-iris technology. Managing the volume of light hitting the sensor is a fundamental challenge in surveillance engineering, as cameras must perform consistently regardless of the environmental conditions. The iris, acting much like the human pupil, sits behind the lens elements and modulates the aperture diameter to control exposure. When a lens is wide open, it collects the maximum amount of light, which is ideal for low light performance, but frequently leads to significant depth of field limitations. Conversely, stopping down the iris increases the depth of field, bringing more of a scene into focus. Yet this approach introduces its own set of physics-based hurdles. If the aperture becomes too small due to high light intensity, light rays begin to interfere with each other at the edges of the iris blades, which is a phenomenon known as diffraction. Diffraction degrades image resolution, resulting in a perceptible softness or blurriness that renders fine details, like facial features or license plates, unrecognizable. Therefore, the engineer's goal is to find the exact aperture setting that balances sufficient exposure with optimal sharpness without triggering diffraction. Traditional DC iris lenses have served the security industry for years, relying on a two-coil system that reacts to a control signal from the camera. In this setup, the camera monitors the video signal, detects if the image is too bright or too dark, and sends current to the motor to either open or close the iris. While effective to a point, the DC iris mechanism suffers from an inherent lack of precision because it essentially operates as a blind feedback loop that is prone to oscillation. Under fluctuating light, the iris often hunts for the correct position, leading to periods where the exposure is either overcorrected or undercorrected. Furthermore, these mechanical systems offer no feedback to the camera software regarding the actual physical position of the iris blades. Because the camera does not know exactly how far open or closed the iris is at any given moment, it cannot reach the optical sweet spot that maximizes contrast and resolution across the scene. This is where Axis proprietary P-iris technology fundamentally changes the equation by introducing a stepper motor and a sophisticated software-controlled feedback loop. Unlike the analog nature of DC iris, P-iris allows the camera to exercise exact, micro-step control over the physical aperture opening. The camera software constantly calculates the optimal iris position based on both the light intensity and the lens characteristics, ensuring that the aperture is never restricted to a point where diffraction ruins the image quality. By preventing the iris from closing beyond the diffraction limit, P-iris maintains a superior depth of field and consistent sharpness across a much wider range of lighting conditions. The algorithmic superiority here lies in the synchronization between the image processing engine and the stepper motor, which removes the guesswork associated with historical lens technology. When deploying systems in environments where lighting shifts dynamically throughout the day, the reliability of P-iris ensures the camera maintains the highest possible image clarity without requiring manual intervention from a technician. Selecting hardware that incorporates P-iris is often a decisive factor in projects where high-resolution detail is non-negotiable. By moving away from the compromises of auto-iris lenses and embracing the digital precision of P-iris, we move into the realm of deterministic image quality. You are no longer fighting the physical limitations of the lens. Instead, you are leveraging software to maximize the optical performance of the glass. This transition ensures that the camera remains a reliable analytical tool rather than a passive observer that loses performance whenever the sun changes position or clouds pass overhead. As we continue through our study of image quality, keep these concepts in mind as they form a building block for everything related to exposure control and visual clarity. I look forward to discussing these technical concepts further as we transition into our next area of focus. Welcome back. Today we are exploring the electromechanical complexities of pan-tilt zoom mechanisms and their role in sophisticated surveillance deployments. At the core of an effective PTZ camera lies the intricate interplay between precision motors and reliable data transmission interfaces. Unlike fixed cameras, A PTZ unit must facilitate continuous 360-degree panning without the risk of cable fatigue or internal connectivity loss. This is typically achieved through the integration of slip rings, which are electromechanical devices that allow the transmission of power and electrical signals from a stationary structure to a rotating assembly. Without these conductive rings and contact brushes, the cabling would inevitably twist and break after a few complete rotations. Engineers must therefore select materials that minimize resistance while maintaining signal integrity across high-speed data protocols like Ethernet. Reliability in these components is non-negotiable for cameras exposed to constant operation or rapid repositioning cycles. Mechanical durability represents the baseline requirement for any hardware intended for long-term field use. Precision movement depends heavily on the motor topologies and gearing systems chosen for the tilt and pan axis. High-end PTZ units often employ stepper motors or brushless DC motors, which allow for granular control over position and velocity. These motors are frequently coupled with high-precision gearboxes to translate rotational force into smooth mechanical articulation. When a camera moves, the goal is to eliminate jerky transitions and backlash, which occurs when there is excess play between the gears. A professional-grade system compensates for this by using anti-backlash gears or digital feedback loops that calibrate the motor's stop point with surgical accuracy. This precision ensures that when a preset is triggered, the camera returns to the exact desired coordinates every single time. Consistent mechanical repeatability is the hallmark of a quality PTZ deployment. Effective programming of these mechanisms involves balancing preset automation with guard tour functionality. A preset is essentially a stored coordinate set consisting of specific pan, tilt, and zoom values that the camera can recall instantaneously. Guard tours extend this concept by chaining multiple presets into a programmed sequence that the camera follows automatically, often with specific dwell times at each location. For advanced integrators, the true power emerges when these mechanical presets are married to video analytics. For instance, an object detection algorithm can trigger a PTZ unit to autonomously track a moving subject across a wide geographical area. However, it is essential to manage the expectations regarding mechanical latency, as the physical displacement of the camera body always introduces a measurable delay between a detected event and the lens reorienting to follow it. Environmental factors significantly complicate the operation of high-performance PTZ cameras. When a camera is positioned at maximum zoom, even minor environmental vibrations are amplified, often leading to jittery or unusable footage. This highlights the necessity of rigid mounting brackets and intelligent image stabilization software that can compensate for these external tremors. Furthermore, the internal mechanical components must withstand extreme temperature fluctuations and humidity without the lubricants hardening or the seals failing. Environmental durability is not merely about protecting the lens. It is about ensuring that the internal gear train continues to function despite years of exposure to rain, wind, and thermal stress. When selecting these assets, one must always evaluate the mechanical assembly as the primary point of failure. See you in the next lecture. Welcome to our dedicated module on image stabilization, where we examine the technical mechanisms required to ensure video clarity in unstable environments. We will focus our attention on the practical trade-offs between physical and algorithmic approaches to vibration mitigation. When we deploy surveillance cameras on poles, bridges, or industrial structures, we are almost inevitably fighting the laws of physics. Mechanical vibrations caused by wind or heavy machinery translate directly into image blur, which complicates forensic analysis and forces video codecs to work harder. When a frame is blurry, the encoder cannot efficiently predict the motion between frames because the entire field of view is shifted or smeared. This leads to an increase in high-frequency data, which manifests as unexpected bandwidth spikes. If we want to maintain both forensic integrity and network efficiency, selecting the correct stabilization method according to the installation type is a core technical requirement. Optical image stabilization, or OIS, tackles this challenge by addressing the problem at the hardware level before the light even hits the sensor. In an OIS-capable camera, the lens element is physically suspended and adjusted by motors or actuators that counteract external tremors. Think of it as a gimbal mechanism built into the optical assembly, which is incredibly effective at neutralizing high-frequency, low-amplitude shakes. Because the compensation happens physically, the raw image data arriving at the sensor is already stable. This is a significant advantage because it preserves the full resolution of the sensor, as we are not sacrificing any pixels to perform a digital transformation. For high-end installations where every pixel must be pristine, OIS is usually the preferred, albeit more expensive, choice. Electronic image stabilization, known as EIS, takes an entirely different approach by relying on internal gyroscopic sensors to detect camera movement. Once the movement is identified, the camera system uses software algorithms to process the incoming image stream in real time. The logic essentially shifts the frame within the larger captured canvas to counteract the vibration detected by the sensors. However, there is a fundamental cost to this process, specifically that the system must crop the image around its edges to create a buffer area for those adjustments. By cropping the edges, the camera effectively reduces its field of view, which you must always account for during the design phase. From a software perspective, EIS is highly flexible, as it can be tuned to ignore specific movement patterns, but it relies on processing power and incurs a slight latency penalty while the image is buffered and digitally aligned. The choice between these two approaches hinges heavily on the specific environmental variables of your deployment site. OIS is generally superior for dealing with the constant, rapid vibrations found in industrial contexts or near high-traffic roadways. EIS, while potentially less precise for extreme vibrations, offers greater versatility for pole-mounted cameras exposed to sustained wind loads or mechanical swaying. There is also no rule stating these technologies cannot theoretically coexist, but in practice, you are often choosing the hardware that best fits the physical reality of the mount. If you install a camera that lacks either form of stabilization on a structure prone to sway, you are essentially guaranteeing that your recording platform will suffer from increased storage costs and degraded video quality. You must evaluate the vibration profile of the deployment site before finalizing your hardware specification to ensure the selected model can handle the environmental instability. Always remember that stable video is the prerequisite for efficient compression and reliable motion detection. If the camera is constantly shaking, the motion detection system may trigger false alarms, which waste resources and hampers the effectiveness of your security operators. By mastering how to specify hardware with proper OIS or EIS, you ensure that the video stream remains usable for forensic teams, while also keeping your network traffic manageable. This balance of physical lens adjustment and algorithmic correction is what elevates a basic CCTV installation into a professional network video solution. We'll see you in the next lecture. Welcome to our deep dive into thermal imaging, where we shift our focus from visible light to the detection of infrared radiation for mission-critical surveillance. Thermal imaging represents a fundamental departure from traditional optical cameras because it perceives heat rather than reflected light. While an optical sensor relies on photons in the visible spectrum to construct an image, a thermal camera measures the long-wave infrared energy emitted by objects. This mechanism is what allows thermal solutions to function effectively in total darkness, through thick smoke, or during heavy fog. Because every object with a temperature above absolute zero emits some level of infrared radiation, the thermal sensor becomes an incredibly powerful tool for perimeter defense. In environments where normal illumination is either impossible to maintain or physically obstructed, thermal imaging offers the only viable path to detection. We achieve this capability by utilizing specialized materials that can transmit infrared energy, distinguishing thermal systems from standard glass lens optics. At the core of this technology, we find the uncooled microbolometer, which has become the industry standard for network-based thermal surveillance. Unlike complex, bulky, and expensive systems that require liquid cooling to reach optimal sensitivity, the uncooled microbolometer sensor is compact and reliable. It comprises an array of pixels made from materials that change their electrical resistance when heated by incoming infrared radiation. As these sensors absorb radiation, the internal temperature fluctuates, and the resulting signal is processed into the grayscale imagery we see on our screens. This technology is robust, requiring little to no maintenance, and is ideally suited for continuous uptime in rugged outdoor deployments. It effectively bridges the gap between high-performance defense systems and the practical, cost-effective requirements of modern network video surveillance. To fully appreciate the performance of these sensors, we must discuss a key metric known as noise equivalent, temperature difference, or net-D. This value quantifies the sensitivity of the camera by measuring the smallest temperature difference that the sensor can resolve. A lower net-D value implies higher sensitivity, allowing the camera to perceive minor thermal contrasts, even in environments with very low background variance. If you are designing a system for a vast, uniform landscape, a camera with an excellent net-D rating is essential for distinguishing human heat signatures from the terrain. This thermal contrast is what drives the effectiveness of downstream video analytics, as the algorithm relies on the distinct separation between the target and the ambient background temperature. When the net-D is optimized, the analytics engine can isolate heat signatures with extreme precision. While standard optical cameras use glass lenses, thermal imaging requires specialized materials because glass is opaque to long-wave infrared light. This is why we almost exclusively use germanium for thermal lenses, as it is uniquely transparent to the infrared spectrum used for heat detection. Germanium lenses are expensive to manufacture and fragile, but they are absolutely necessary to ensure that the radiating heat reaches the detector without significant attenuation. When selecting a thermal lens, you are essentially determining your detection range and field of view, much like with optical optics. However, you must pair this choice with the sensor resolution to maintain the necessary pixel density for your specific detection or identification requirements. The geometry of the scene remains a critical design consideration, even when the underlying physics of the image acquisition changes from visible light to thermal energy. Thermal sensors are the most effective solution for perimeter protection when combined with intelligent analytics because they eliminate the false alarms that plague optical sensors in variable lighting. Optical cameras often struggle with shadows, changing cloud cover, or flashing emergency lights, all of which can trigger a motion mask unnecessarily. Thermal cameras, however, are essentially immune to these common lighting disturbances because they only react to actual temperature gradients. By configuring detection zones that look specifically for the heat profile of a human or vehicle, a security designer can create an incredibly resilient system. This allows for drastic reductions in guard fatigue and incident response times, as operators receive data only when a meaningful thermal event occurs. When integrated into a hardened infrastructure, these principles guarantee reliable detection regardless of the surrounding environmental conditions. See you in the next lecture. Welcome back. Let us explore the complexities of maintaining image usability in environments where lighting is rarely static. In the domain of professional video surveillance, achieving a usable image is less about artistic exposure and more about the rigorous preservation of forensic detail. Sunlight shifts across the sky, interior lights cycle on and off, and artificial sources introduce high-contrast interference that can render a poorly configured camera blind. To manage these variations effectively, we must understand the fundamental triad of exposure: shutter speed, gain, and iris aperture. Each element serves a specific purpose, yet they often work in opposition when it comes to balancing light sensitivity with signal clarity. For instance, increasing gain amplifies the signal to illuminate a dark scene, but it simultaneously magnifies the noise floor, which can obscure critical details like facial features or license plates. Conversely, a slow shutter speed improves low-light capture by keeping the sensor exposed for a longer duration, but this inevitably introduces motion blur. An engineer must weigh these trade-offs, preferring a noisier image that retains the ability to identify a subject over a smooth, grain-free image that is fundamentally motion-blurred and useless for verification. Consider the logistical nightmare of a warehouse loading dock, where a camera must transition from a bright, daylight-washed exterior to a dim interior. This situation presents a rapid light transition that tests the dynamic range limits of any standard sensor. If the camera is left in full auto exposure, the algorithm will likely prioritize the average brightness of the scene, causing the exterior entrance to blow out into pure white, while the interior details remain hidden in deep shadows. To mitigate such occurrences, we utilize exposure zones, which allow us to tell the camera's internal processor to ignore the brightest part of the frame, the sunlit doorway, when calculating the appropriate exposure values. By constraining the metering area, we ensure the camera maintains focus on the critical surveillance area, even while the surrounding environment remains visually chaotic. These software-based adjustments are the first line of defense before we even consider physical hardware interventions. When we encounter extreme contrast beyond what basic metering can handle, we must address the physics of the optical path itself. Backlighting, where a subject stands in front of a significantly brighter background, is a classic scenario where the camera's aperture might attempt to compensate for the background, leaving the subject as a silhouette. In these cases, we evaluate the camera's ability to handle high dynamic range or look toward physical iris adjustments that prioritize depth of field and light throughput. If an aperture is set too wide, we might suffer from a shallow depth of field, causing objects in the foreground or background to drift out of focus exactly when we need them to be sharpest. Simultaneously, we must be wary of internal reflections or glare caused by artificial lights hitting the lens elements, which manifests as haze or phantom light spots. Choosing the correct mounting position to minimize light hitting the lens directly is often more effective than attempting to fix contrast issues through software gain alone. Environmental factors such as intense glare from wet pavement or highly reflective building facades further complicate our ability to retrieve actionable data. These reflectances introduce erratic light levels that fluctuate with the weather, requiring us to set hard limits on exposure parameters. While automatic exposure provides convenience, it can be dangerous in security applications because it is reactive and can be tricked by temporary bright light sources like car headlights. By setting a maximum allowable gain or a fixed shutter range, we prevent the camera from overcorrecting and introducing excessive noise or lag. We are essentially defining the operational boundaries within which the camera is allowed to function. This approach ensures that when an event occurs, the camera is already configured for the worst-case scenario, rather than struggling to catch up while the subject passes through the field of view. See you in the next session. Welcome back. Today, we are going to explore the mechanics behind Lightfinder technology and how it changes our approach to low-light surveillance. In traditional security camera deployments, the arrival of nightfall usually signals a transition from color video to a monochrome infrared state. This shift is a compromise, as the loss of color information significantly impairs forensic utility, making it harder to discern specific details like the color of a suspect's jacket or the hue of a vehicle. Lightfinder technology disrupts this status quo by utilizing a specialized combination of high-sensitivity sensors and sophisticated image processing. The sensor itself is designed with larger pixels or enhanced hardware architecture that gathers more photons per frame than a standard digital image sensor. When you combine this with a precision-engineered lens, often characterized by a large aperture that lets in substantial light, the system can operate effectively in environments where the human eye struggles to see. It is not magic, but rather a disciplined application of optical science designed to sustain image fidelity well beyond the reach of standard hardware. To understand the core advantage, we must look at how the system-on-chip architecture handles the raw data stream coming from the sensor. In low-light conditions, typical sensors introduce a significant amount of electrical noise, which software normally cleans up by applying heavy blur filters that destroy fine detail. Lightfinder algorithms instead prioritize the preservation of edge information and color chrominance even in extremely dim, ambient-lit environments. By employing noise suppression techniques that are temporally aware, the camera can distinguish between true movement and the random pixel fluctuations we call sensor noise. This allows for a clean image where color information is retained, which is arguably one of the most critical aspects of forensic evidence. When identifying a suspect, knowing that a car is red versus black, or that a jacket provides a specific color contrast against the background, often becomes the deciding factor in successful investigations. The practical implications of this technology are most evident when we compare them to the standard day-night monochromatic approach. When a camera switches to infrared, it is essentially shifting to a different frequency spectrum, rendering all colors as grayscale intensities. While this allows the camera to see in total darkness with the help of an IR illuminator, you lose the ability to capture specific attributes that are only visible in the visible spectrum. Lightfinder allows the camera to hold on to color data as long as humanly possible, often providing a usable image in extremely darkened parking lots or perimeter fence lines where external lighting is minimal but present. For a system designer, this means you can often reduce the reliance on supplemental white light or IR illuminators, which can sometimes cause glare or blobbing issues when subjects come too close to the lens. By maintaining color accuracy, we essentially extend the operational performance of our security network into the late hours, providing the video management system with richer data for both human review and analytics. We should also consider that these technologies require specific camera placement and environmental configurations to reach their full potential. While a camera equipped with this optical capability is far more sensitive, it still relies on at least some minimal ambient light to function as intended. If you are designing for a pitch-black environment with zero ambient photon sources, even the best sensor cannot reconstruct color information from nothing. That is where supplemental lighting or thermal cameras would become a necessary secondary design consideration. However, in urban settings or areas with street lighting, the technology acts as a force multiplier for the existing visual environment. When selecting a camera, the decision to opt for this feature should always be predicated on the forensic requirement for color differentiation. If the goal is simply to verify that something triggered a motion event in total darkness, a standard IR approach might suffice. But for identification, the color fidelity offered by this technology is the superior engineering choice. See you in the next lecture. Welcome to our look at infrared lighting. In this chapter, we will master the technical nuances of OptimizedIR technology to ensure your surveillance remains effective in total darkness. OptimizedIR represents a significant shift from the traditional approach of using bulky, external infrared floodlights, which often suffer from uneven illumination and synchronization issues. When you integrate IR LEDs directly into the camera housing, the light source shares the same optical axis as the sensor, which provides a more natural and controlled beam. A primary challenge in nighttime surveillance is the inverse square law, where light intensity drops off rapidly as the subject moves further away from the lens. By dynamically adjusting the LED output based on the camera's current focal length, the system ensures that the illumination angle always matches the field of view. Imagine a camera zoomed in on a parking lot entrance. A static illuminator would waste energy by lighting the walls and ground instead of the target, whereas OptimizedIR concentrates the photon density exactly where it is needed. This level of synchronization eliminates the common problem of tunnel vision, where only the center of the frame is visible, or conversely, the overexposure of nearby objects. Understanding the physical limitations of infrared wavelengths is crucial for any network video professional, as sensors perceive NIR light differently than human eyes. While we categorize infrared as invisible, high-power LEDs can sometimes produce a faint red glow, a trade-off that designers must balance depending on the covert requirements of the installation site. Thermal management also plays a far more significant role here than invisible light modules, because LED arrays generate internal heat while consuming power from the same rail that drives the sensor and processing unit. If you do not account for the power budget of the integrated IR, you risk exceeding the limitations of the power over Ethernet switch, potentially leading to instability during the transition from day mode to night mode. The internal circuitry must intelligently manage the duty cycle of these emitters to prevent the camera housing from overheating, which could lead to sensor noise or, in extreme cases, electronic degradation. Successful deployment requires you to verify that the camera's power class is compatible with the total current draw, especially when operating in cold environments where internal heaters might also engage. The issue of IR reflection from nearby surfaces is perhaps the most frequent cause of poor image forensic quality in zero-lux environments. When IR light hits a reflective surface like a white wall or a metal sign close to the camera, it bounces back toward the lens and creates a bloom effect that completely washes out the rest of the scene. Advanced cameras mitigate this by utilizing software-defined masks or by varying the intensity of individual LEDs within the array to reduce the reflection without sacrificing the distance of the rest of the view. You must also consider the positioning regarding walls and ceilings, as mounting a camera in a corner inevitably leads to these reflection problems if the IR beam is wide enough to catch the adjacent surface. By fine-tuning the illumination width through the camera's web interface, you can physically constrain the IR beam to cover only the subject area of interest. This precision not only improves the overall contrast of the image, but also makes the system more energy efficient, which matters when you are planning an installation that relies on limited bandwidth and power delivery infrastructure. We will move on to the next topic now. Welcome back, and let us now turn our attention to the critical task of mitigating motion blur within your surveillance architecture. This chapter will provide you with the technical foundation needed to ensure your video evidence remains sharp and actionable, even when subjects are moving at significant velocities. Motion blur is essentially a consequence of the interplay between the shutter speed of the camera and the physical speed of the object moving across the frame. When an object traverses a distance across the sensor during the time the shutter is open, that movement is captured as a smeared trail across multiple pixels. To minimize this, we must enforce a shorter exposure duration, effectively freezing the subject in space. However, light acts as a finite resource in this equation. By shortening the exposure time, we inevitably limit the number of photons that hit the sensor, resulting in a darker image. To compensate for this loss of light, the camera system typically increases its gain or signal amplification, which introduces a different set of challenges, specifically electronic noise. In high-stakes environments, such as license plate recognition or monitoring high-speed transit, the priority is almost always the identification of the target rather than the overall aesthetic brightness of the image. For license plate recognition, you are often dealing with vehicles traveling at significant speeds, meaning the shutter speed must be incredibly fast to avoid the smearing of characters. Calculating the required shutter speed requires looking at the speed of the object, its distance from the camera, and its angle of travel. An object moving perpendicularly to the camera's view will require a much faster shutter speed than one moving directly toward or away from the camera. This is because the lateral movement creates the greatest displacement across the sensor's individual pixel rows. To maintain adequate image quality when forcing such aggressive shutter speeds, we must consider the hardware configuration of the system. Since we have effectively strangled the amount of light entering the camera, we must compensate through physical means rather than artificial gain amplification. This often involves selecting an aperture that allows for a larger light intake, assuming your depth of field requirements remain satisfied. When a larger aperture is not sufficient to compensate for the reduced light gathering time, you must introduce auxiliary lighting to the scene. Infrared or white light illuminators provide the spectral energy necessary for the sensor to resolve detail without relying on high gain settings that can obscure fine texture. We should approach these configurations with a degree of mathematical rigor rather than trial and error. If you determine that a shutter speed of 1/1000th of a second is necessary to stop the motion of a vehicle, you must then verify that your chosen illumination source provides enough lux at that specific speed on the target plane. Failure to do so will result in an image that is technically free of motion blur, but contains too little signal variance to perform any meaningful analysis. This is a common point of failure in system design where the camera is perfectly capable, but the environmental lighting conditions are insufficient to support the high shutter speeds demanded by the installation's security objectives. The trade-off here is ultimately one of data integrity versus signal-to-noise ratios. You are choosing to sacrifice raw brightness for the structural integrity of the moving target. By standardizing these calculations during the design phase, you ensure that the forensic potential of the video is realized. Your goal is to deliver an image that provides enough clarity to satisfy the requirements of the end user, whether that be human operators or automated license plate recognition software. When both the lighting and the shutter speed are aligned, the resulting stream becomes a reliable tool for security, free from the artifacts that historically rendered moving subjects as unusable, ghostly shapes. I look forward to our next discussion as we continue to refine your design practices. Hello, and welcome back. Today, we are going to explore the mechanics behind noise reduction algorithms in network video systems. In digital imaging, noise is an inevitable byproduct of signal amplification when light levels drop, manifesting as random variations in brightness or color information across the image sensor. Because these variations are non-periodic and random, they present a significant challenge for video compression codecs, which mistake this high-frequency noise for legitimate image detail. Consequently, the encoder attempts to preserve this noise, leading to an inflation of the output bitrate because the compressor cannot effectively categorize the data as redundant. Effective noise reduction, therefore, serves a dual purpose by enhancing human interpretability and significantly reducing the bandwidth required to stream the video. We must treat these algorithms as a trade-off mechanism where we actively decide which signals are valid visual information and which signals constitute electrical interference. Achieving this balance requires a firm understanding of how different architectures process pixel data across both time and space. 2D spatial noise reduction operates strictly within the boundaries of a single frame, analyzing the relationship between a target pixel and its immediate surroundings. The algorithm generally applies mathematical smoothing, such as Gaussian or median filtering, to assess the luminance and chrominance values of neighboring pixels. If a pixel deviates significantly from the median of its neighbors, the algorithm assumes this deviation is noise and replaces it with a computed average. This approach is computationally efficient, making it suitable for hardware-constrained environments that lack deep buffers or excessive processing overhead. However, 2D spatial filtering carries the distinct disadvantage of potential detail loss, as the algorithm struggles to differentiate between high-frequency noise and fine structural edges, such as a sharp corner or a thin wire. When applied too aggressively, spatial filtering can soften the image, resulting in a loss of forensic sharpness that might be necessary for identification. In contrast, 3D temporal noise reduction utilizes the redundancy of information across a sequence of frames, which is inherently more effective for static scenes. Because true noise is random and changes with every clock cycle of the sensor, comparing sequential frames allows the processor to determine which data points remain static and which are transient anomalies. If a pixel value remains relatively stable across multiple frames, the temporal filter increases its confidence that the current value is accurate and applies a weighted average to smooth out the jitter. This method is exceptionally powerful for low-light scenarios where the noise floor is high, as it cleans the video signal without necessarily blurring the edges of objects. Despite its efficacy, 3D filtering introduces the risk of ghosting or smearing whenever an object moves rapidly through the frame. The algorithm effectively buffers previous states, so when a subject moves, the temporal lag can result in trailing artifacts where the subject previously existed. Calibrating these thresholds requires an integrator to weigh the operational requirements of the installation against the existing constraints of the network infrastructure. If the primary goal is high-frequency motion detection or forensic evidence at distance, excessive noise reduction may be detrimental because it hides transient details that are essential for analysis. Conversely, in a deployment where storage costs and network bandwidth are the primary drivers, enabling more aggressive temporal reduction can yield massive savings by allowing the encoder to achieve higher compression ratios. One must also consider the interaction between noise reduction and the camera's shutter speed. If the camera is already struggling with motion blur due to a slow shutter, adding aggressive 3D noise reduction may exacerbate the appearance of motion-related artifacts. Therefore, the implementation of these algorithms is rarely a set-and-forget task, but rather a deliberate act of engineering that must be tuned to the specific environmental and temporal dynamics of the installation site. Choosing the correct intensity involves testing the output within the actual lighting conditions of the scene being monitored. Most Axis cameras provide a slider or a range of settings, and it is a common mistake to push these limits to their maximum in an attempt to achieve a perfectly clean picture. You should instead look for the point of diminishing returns where the noise is suppressed sufficiently for the stream to become manageable without destroying the integrity of fine textures like clothing patterns or facial features. Always verify the result by simulating realistic movement in the scene to ensure that the temporal reduction is not creating objectionable drag or ghosting around moving subjects. By carefully balancing these spatial and temporal components, you ensure that the video remains both visually intelligible for personnel and highly efficient for the network infrastructure. See you in the next lecture. Hello. Today we are diving into the technical nuances of network bandwidth management for video surveillance systems. Accurately calculating network bandwidth is a foundational skill for any professional architecting secure and reliable video infrastructures. We will explore the mathematical variables that influence bitrate, examine the difference between constant and variable bitrate deployments, and leverage professional tools to ensure network stability. By the end of this session, you will possess the ability to model complex camera configurations against existing network throughput constraints to prevent performance bottlenecks. When we approach bandwidth calculation, we must view the camera not just as an optical device, but as a data generator producing a continuous stream of packets. Bitrate is primarily driven by the resolution of the image, the frame rate, the compression standard applied, and the inherent complexity of the scene being monitored. Higher resolutions naturally demand more bits per second, but the relationship is not always linear due to the way compression algorithms handle spatial detail. Frame rate also acts as a multiplier. Doubling the number of frames per second will directly increase the expected bandwidth consumption if all other settings remain constant. However, the most unpredictable variable is scene content, specifically the level of motion and detail present in the field of view. A camera pointing at a static wall generates significantly less data than a camera monitoring a busy intersection, even if the resolution and frame rate settings are identical. Compression standards such as H264 and H.265 are essentially mathematical models designed to strip away redundant information before transmission. H.265 is generally more efficient at maintaining image quality at lower bit rates, yet it requires more processing power from the encoder, which is a trade-off that should be considered during the system design phase. When selecting a bitrate configuration, you must choose between constant bitrate, or CBR, and variable bitrate, or VBR. CBR forces the stream to stay within a strict throughput limit, which makes network load predictable for IT administrators, but it may sacrifice video quality during high-motion events. VBR, conversely, allows the encoder to adjust the bitrate based on scene complexity, ensuring consistent visual fidelity while letting the throughput fluctuate. In high-security environments, VBR is often preferred for quality, provided that the network infrastructure possesses sufficient overhead to accommodate potential traffic spikes. Predicting bandwidth consumption requires moving beyond simple estimations and toward precise mathematical modeling using documented variables. You should start by calculating the average bit rate based on standard activity, but you must also define a peak bitrate scenario to ensure the network does not reach saturation point. If the network becomes saturated, the resulting latency, packet loss, and dropped frames will undermine the integrity of your security footage, effectively rendering the system useless during critical incidents. To manage this risk, we rely on dedicated design tools that take manufacturer-specific algorithms into account, allowing us to perform capacity planning with a higher degree of certainty. These tools aggregate input from multiple camera streams to provide a holistic view of the total network load imposed on switches and gateways. Ignoring this proactive engineering step is a recurring source of preventable infrastructure failures in enterprise installations. Proactive network engineering means that you are designing for the worst-case scenario rather than the average, ensuring that your backbone remains stable during busy periods. Even if an office environment has a theoretical capacity of 1 gigabit, the sustained throughput of high-definition video streams can quickly consume that headroom. You need to account for not just the cameras, but also the management traffic from VMS servers and client viewing stations that pull devices simultaneously. When calculating the total load, it is vital to apply a safety margin to your estimates, as real-world network overhead and protocol headers often account for a higher percentage of the traffic than initially anticipated. By systematically modeling these flows, you establish a predictable baseline that allows for future expansion without performing a total infrastructure overhaul. This rigorous approach is what distinguishes a robust, enterprise-grade video system from one prone to erratic behavior. See you in the next lecture. Welcome back to our exploration of network technologies. In this session, we will examine the principles of power over Ethernet and how it facilitates the deployment of surveillance hardware. Power over Ethernet, or PoE, is fundamentally an elegant solution to a common infrastructure problem: how to power remote devices without requiring a dedicated electrical outlet at every installation point. By leveraging the existing copper conductors and standard twisted pair Ethernet cabling, we can transmit both electrical power and data simultaneously. The IEEE 802.3 standards govern this process, ensuring that the power sourcing equipment and the powered device communicate effectively before any significant current is applied. This handshake mechanism is critical because it identifies the power class of the device, preventing potential damage to hardware that does not support PoE. Understanding these standards is not merely an academic exercise. It is the foundation of reliable system design where camera uptime is non-negotiable. When you consider the vast array of surveillance components, you realize that the cabling infrastructure effectively acts as a bus system for energy management. It is a system built on robust negotiation and safety, designed to prevent catastrophic failure while simplifying the physical cabling of a facility. To understand the practical limits of this technology, we must contrast the evolution of the IE release standards, starting with 802.3 AF, which provides up to 15.4 watts of direct current at the source. While sufficient for fixed dome or bullet cameras, this is often inadequate for sophisticated units that require heaters, blowers, or motorized pan-tilt zoom mechanisms. Here is where the 802.3 at standard, commonly referred to as PoE+, becomes necessary by pushing the available power up to 30 watts. For even more demanding scenarios, such as high-performance PTZ cameras with complex environmental housing, the 802.3 BT standard allows for significantly higher power budgets. These classifications dictate exactly how much current a switch port must be prepared to deliver, and ignoring these specifications almost invariably leads to reboot cycles during peak power draw. If a camera suddenly goes offline when its internal heater kicks in during a cold night, you are likely looking at a power budget or classification mismatch. The hardware is trying to draw more energy than the switch was negotiated to provide, resulting in a state of constant power cycling. Designing a robust surveillance network necessitates a careful calculation of the total power budget available on your network switches. It is a common mistake to assume that every port on a high-density switch can supply the maximum power defined by the highest enabled standard simultaneously. You must aggregate the actual power consumption values of every connected device and ensure the total does not exceed the switch's power supply capacity. Furthermore, we must account for voltage drop, which occurs as a direct result of electrical resistance over the length of the Cat5e or Cat6 cabling. As the cable run approaches the 100-meter limit, the effective voltage at the camera may decrease, potentially causing poor performance or failure to initialize. When your physical infrastructure requirements force you to exceed these limits, you must consider the strategic deployment of midspans or active extenders. These devices act as intermediaries that inject power or regenerate the signal, allowing you to bridge the gap between regional distribution closets and isolated remote camera locations. Troubleshooting power negotiation failures requires a disciplined approach, as the issue can often reside in the physical layer before it manifests in the software stack. If a camera fails to power up, your first step should be to audit the physical cable for continuity and resistance, especially if the run was recently repurposed or extended. Thermal dissipation also plays an unexpected role in high-density installations, particularly when switches are mounted in poorly ventilated cabinets. Excessive heat within a rack can reduce the efficiency of internal power components, leading to intermittent failures that are notoriously difficult to diagnose without monitoring the environmental telemetry. You should always maintain a record of the actual wattage drawn by each device compared to the theoretical nominal value during system startup. This data is invaluable during root cause analysis, as it allows you to distinguish between an intentional safe mode shutdown and a faulty power supply component. By maintaining a clean, well-documented power plan, you ensure that the surveillance system remains resilient against the minor fluctuations and hazards inherent to large-scale network deployments. I look forward to discussing the next topic in our series. Welcome back to our journey through the network infrastructure requirements for modern video surveillance systems. In this session, we will focus exclusively on switch configuration parameters essential for supporting stable, high-performance network video. To build a professional-grade video surveillance network, you must understand the role of the managed switch as the backbone of your data transport architecture. While standard office environments might function adequately with unmanaged switches, IP video demands deterministic behavior to prevent packet loss and jitter. The primary mechanism for traffic management at the data link layer is the implementation of virtual local area networks, or VLANs. By isolating video traffic onto a dedicated VLAN, you effectively reduce the size of individual broadcast domains and prevent latency spikes caused by broadcast storms from general corporate traffic. When configuring these segments, you should ensure that access ports connecting to access cameras are explicitly assigned to this video-specific VLAN while tagging frames accordingly for transit across trunk ports between switches. Beyond simple segmentation, the resilience of your network depends on the proper application of the spanning tree protocol, or STP. In a redundant network topology where multiple paths exist, loops can quickly overwhelm switch buffers and consume all available bandwidth, leading to catastrophic video transmission failures. You must ensure that STP, or its more modern variations like Rapid Spanning Tree Protocol, is active and configured with appropriate bridge priorities to ensure a predictable topology. Furthermore, for high-density camera deployments, individual copper gigabit uplinks often become bottlenecks when multiple high-resolution streams aggregate into a single path. Link aggregation, typically implemented via the 802.3 AD standard, allows you to combine multiple physical ports into a single logical channel, providing both increased throughput and the benefit of physical redundancy if one cable fails. Security at the edge is another critical dimension of enterprise switch configuration that is frequently overlooked during the initial integration phase. Implementing port security allows you to limit the number of devices allowed on a specific switch port by strictly controlling the MAC addresses granted access. This prevents unauthorized devices from simply plugging into an exposed camera drop in a hallway or parking lot to gain access to the internal network. While this adds a layer of administrative overhead, it is a necessary practice when hardening an access device deployment against physical tampering. You should also consider disabling unused ports on the switch to minimize the physical attack surface of the network, as any open port serves as a potential gateway for malicious activity if left unprotected. Final, and perhaps most vital aspect of our discussion involves quality of service, or QoS, which ensures that our video packets receive preferential treatment during periods of network congestion. We achieve this by utilizing differentiated services code point, or DSCP markings in the IP header of the transmitted frames. When you configure your switches to recognize these markings, the system can prioritize video streams over standard background traffic like file transfers or web browsing. Without proper QoS mapping, a spike in non-critical data can easily induce latency or jitter, which manifests as frozen images or visual artifacts in your video management system. You must ensure that your switch infrastructure is configured to trust these DSCP markings and propagate them throughout the switching fabric to guarantee a consistent, low-latency path from the sensor to the storage server. I look forward to our next session together. Welcome back. In this chapter, we explore IP addressing strategies which are critical to maintaining scalable and manageable network video environments. When we design a surveillance network, the method by which we assign IP addresses defines the longevity and maintainability of the entire system. At the most fundamental level, we are choosing between the maturity of IPv4 and the vast address space afforded by IPv6. While IPv4 remains the standard in most current access installations, we must contend with its limitations, primarily the exhaustion of available addresses and the necessity for subnets to segment traffic. Subnetting is not merely a task of division, but a strategic mechanism to confine broadcast traffic, which is essential to prevent camera discovery protocols like ARP from overwhelming the network fabric. By applying variable length subnet masking, or VLSM, we can tailor the size of our address blocks to fit specific hardware clusters, effectively reducing waste and ensuring that address blocks grow proportionally with the installation. Proper segmentation ensures that a network glitch in one segment of a warehouse does not propagate to the administrative floor or the emergency operations center. This level of logical isolation is the hallmark of a professional installation where deterministic routing is preferred over the chaotic flat topology often found in smaller, ad hoc setups. We must treat every network segment as a unique container that requires its own set of rules, documentation, and address hierarchy. The choice between static assignment and dynamic addressing via DHCP poses a significant architectural decision that impacts how we manage large-scale surveillance fleets. For critical infrastructure devices such as recording servers, encoders, and primary management interfaces, we almost exclusively rely on static IP addresses to guarantee predictable communication paths. Dynamic addresses are efficient for transient hardware or standard client workstations, but they introduce a dependency on a DHCP server that must be treated as a single point of failure in a security-critical environment. If the DHCP server becomes unavailable, new cameras will fail to initialize, potentially creating blind spots in your surveillance grid that go unnoticed until an incident occurs. Therefore, even when DHCP is used for convenience, it is best practice to employ DHCP reservations based on the unique MAC address of the device, creating the illusion of a dynamic address while maintaining the certainty of a static one. Meticulous documentation of these assignments is not optional. It is the backbone of your support strategy, ensuring that when an issue arises, you know exactly which device corresponds to which address without fumbling through scan results. Without a well-maintained IP registry, troubleshooting becomes an exercise in desperation rather than a structured technical response. Remote access and multi-site connectivity introduce the necessity for network address translation and port forwarding, mechanisms that act as the gatekeepers between your secure surveillance network and the outside world. In a typical routing scenario, NA allows us to map internal non-routable addresses to a single public IP, obscuring the internal topology from external entities and providing a thin layer of address-based security. While NA is an essential tool, we must be judicious in applying port forwarding, as exposing camera interfaces directly to the internet is a practice we must strictly avoid due to the inherent security risks. Instead, we should rely on secure routing protocols or encrypted virtual private networks to bridge the gap between remote sites and the central management station, keeping the internal address scheme entirely private. If you must allow remote access, consider using a reverse proxy or an integrated cloud connection service that does not require opening raw ports on your perimeter firewall. These methods ensure that the communication remains authenticated and encrypted, preventing unauthorized parties from hijacking the video stream or manipulating camera settings. Security is not an afterthought in IP addressing. It is integrated into the routing logic itself, protecting the integrity of the data from the sensor all the way to the storage terminal. See you in the next lesson. Hello, it is good to have you back for another technical deep dive into networking dynamics. Today, we are looking at multicast video streams, a mechanism that is fundamental to building scalable surveillance systems that do not choke your network backbone. In a standard Unicast environment, every single client requesting a video feed creates a persistent, individual stream from the camera to the destination. If you have a high-resolution camera and 10 security guards viewing that same feed on their respective workstations, the camera must encode and transmit that video 10 distinct times. This approach quickly exhausts the uplink capacity of the edge switch and places an unnecessary computational burden on the image sensor. Multicast solves this by enabling the camera to send a single stream that is replicated only when and where it is strictly necessary by the network infrastructure. This one-to-many communication model treats the network fabric as the distribution point, moving the heavy lifting away from the camera's own CPU for every individual consumer. The primary challenge we face with multicast is that it is essentially a broadcast-like traffic pattern, which by design tends to flood every port on a layer 2 switch. Without proper management, the camera sends the multicast traffic to the switch, and the switch, oblivious to who actually wants the footage, forwards the packets out every single physical port. This can lead to a state of network saturation where devices entirely unrelated to the video surveillance system become overwhelmed by the sheer volume of unnecessary packets. To mitigate this, we rely on Internet Group Management Protocol, or IGMP, snooping. IGMP snooping allows an intelligent switch to listen to the communication between clients and multicast routers to build a dynamic table of which ports are actually requesting the stream. By implementing IGMP snooping, the switch acts as a filter, ensuring that the multicast traffic is only directed toward ports where an active receiver has explicitly requested the stream. It is important to remember that for IGMP snooping to be effective, both the switch hardware and the network configuration must support it correctly. If you have a mixed environment of managed and unmanaged switches, the multicast traffic will essentially leak, negating the efficiency gains we aim to achieve. Furthermore, you must ensure that there is an IGMP querier present on the network, which is often a function performed by the Layer 3 multicast router. Without a querier periodically asking which devices still require the stream, the switch will eventually time out the membership entries and stop forwarding traffic altogether, leading to a sudden loss of video feed. In architecting these systems, we often encounter the need for multi-subnet routing, which introduces the concept of multicast rendezvous points. In a simple single subnet flat network, the camera and the clients can negotiate group membership directly, but crossing router boundaries requires a more formal rendezvous point. This acts as a common meeting place for multicast sources and receivers to exchange information about the traffic flows. Configuring these points manually or dynamically requires a firm grasp of your overall network topology, as an incorrectly defined rendezvous point results in fragmented streams and intermittent failures. It is common to see scenarios where a video wall client located on a different VLAN simply fails to receive the stream because the multicast routing protocol has not been configured to traverse the gateway. We should also briefly address the address allocation for multicast. Multicast IP addresses reside in the Class D range, specifically from 224.all.all.all to 239.255.255.255. Within this range, there are reserved addresses, and for surveillance applications, you typically operate within the administratively scoped range to avoid collisions with other internal network services. When you configure an Axis camera to stream multicast, you define the multicast destination IP and port, and the camera then joins that group. It is critical to ensure that your address schema remains documented and consistent across all cameras to prevent overlapping traffic that could lead to unpredictable behavior in your video management software. This is particularly relevant when you deal with multiple cameras running simultaneously on the same system architecture. Troubleshooting these environments is almost always an exercise in verifying the Layer 2 and Layer 3 membership states. If a client is not receiving a stream, the first step is to use diagnostic tools to confirm whether the host has sent an IGMP join message and whether the switch has registered that port for the specific multicast group. You might find that the switch port is blocking the traffic because of a security policy, or perhaps the multicast group is being dropped by a firewall configured to treat multicast packets as suspicious traffic. Understanding the flow of these packets from the camera, through the access switch, and potentially across the router core is what separates functional, efficient networks from those requiring constant maintenance. Mastery here allows you to push the boundaries of what is possible in a large-scale deployment. See you in the next lecture. Hello, and welcome back. In this module, we will explore the fundamental mechanics of unicast network traffic and its role in your video systems. We are going to deconstruct how one-to-one communication functions within modern surveillance infrastructures and why it serves as the backbone for most Axis deployments. Unicast is defined by a direct point-to-point connection between a single source, such as an Axis network camera, and a single destination, which is typically your video management system or VMS server. In this architecture, each packet of data is addressed specifically to the unique IP address of the receiving device. Unlike broadcast or multicast methods where data might be sent to an arbitrary group, Unicast establishes a dedicated conversation path. This creates a predictable environment where the communication protocol, often TCP or UDP, governs the reliability of the delivery. When you utilize TCP, the networking stack ensures guaranteed delivery by acknowledging every packet, which is essential for configuration data or critical command exchanges. However, for live video streams, we often favor UDP because it minimizes overhead by stripping away the intensive error correction handshakes required by TCP, thereby prioritizing raw speed and timing over the absolute retransmission of every single lost frame. The primary challenge with unicast transmission emerges when we consider the scaling of modern security systems across enterprise networks. Imagine a single high-definition camera acting as the source for multiple security operators watching the live feed simultaneously. If every operator's workstation requests a separate unicast stream directly from the camera's internal processor must manage each individual connection independently. This leads to an exponential increase in CPU utilization and bandwidth consumption at the source, which can easily exceed the camera's processing capacity if the number of concurrent viewers grows too high. To address this, we introduce the concept of a VMS proxy or a media gateway that acts as a central hub for video distribution. By having the camera send a single unicast stream to the VMS server, the server then replicates and manages the delivery to multiple clients, protecting the camera from being overwhelmed by a flood of repetitive requests. Understanding the nuances of routing is essential for any integrator troubleshooting connectivity bottlenecks within a network video system. Because Unicast relies on specific destination addresses, it is highly sensitive to the configuration of routers, switches, and firewalls throughout the network path. If a routing table is misconfigured, or if there are firewall rules that lack a clear path for the return traffic, the connection will fail, resulting in a black screen despite the camera being powered and technically reachable. You must ensure that your network infrastructure allows for the bidirectional flow required by these protocols, especially when VLANs are present. A common mistake is neglecting the return path for the signaling channel, which prevents the VMS from establishing the initial handshake with the device. By methodically verifying these paths, you can clear the majority of the connectivity issues encountered in day-to-day operations and ensure a stable environment for your Unicast transmissions. Balancing your use of Unicast alongside secondary multicast streams is a common strategy in larger surveillance deployments. Typically, we use Unicast for the primary recording stream from the camera to the storage server, as this provides a reliable, verified data path that the VMS can manage with precision. At the same time, we might configure a secondary multicast stream to provide live viewing capabilities for internal users on the local area network. This hybrid approach allows you to benefit from the guaranteed point-to-point nature of Unicast for recording integrity while leveraging the efficiency of multicast for widespread one-to-many live viewing. The key responsibility for any system designer is to ensure that these two traffic types do not contend for the same finite resources on your network switches. By understanding how to isolate and prioritize these different streams, you gain the ability to build sophisticated, high-performance video architectures that scale effectively as your project requirements expand. I look forward to seeing you in the next lesson. Hello, and let's dive into the core of how modern video surveillance manages to remain efficient. In this chapter, we explore the H264 video compression standard to understand how we balance image fidelity with the realities of storage and network capacity. When we talk about video compression, we are essentially talking about the art of discarding information that the human eye is unlikely to notice while retaining the critical forensic details required for security applications. The H264 standard, also known as Advanced Video Coding or MPEG 4-Part 10, achieves this through a sophisticated combination of spatial and temporal redundancy reduction. Spatial compression focuses on a single image, utilizing algorithms that identify areas of similar color or luminance within a frame, allowing the encoder to store a mathematical representation rather than raw pixel data. This intra-frame process, or iframe generation, provides a complete snapshot of the scene, serving as a vital anchor point for the subsequent video stream. By effectively reducing the data density of each individual frame, the encoder creates a lightweight foundation that satisfies the requirements for high-definition surveillance without overwhelming the connected infrastructure. Understanding this architectural layer is the first step toward optimizing any video management system. Temporal compression is where the H264 standard truly earns its reputation for efficiency by capitalizing on the fact that surveillance video often remains static for long periods. Instead of re-encoding every single pixel for every frame, the encoder generates p-frames, which only record the differences between the current frame and the preceding ones. If a security camera overlooks a quiet hallway, the background pixels remain unchanged, so the stream only needs to transmit the movement of a person walking through that space. B-frames offer even higher efficiency by referencing both past and future frames to interpolate motion, further reducing the size of the stream at the cost of increased computational complexity. This entire sequence, originating from a keyframe and proceeding through these predictive frames, is what we define as the group of pictures, or GOP. By manipulating the GOP length, we define how often the system forces a full iframe, which requires more bandwidth but facilitates faster recovery if a frame is dropped during transmission. The choice of a compression profile, such as baseline, main, or high, determines how much computational power the encoding camera and the decoding client must invest to handle the video stream. The baseline profile is the least resource-intensive, making it compatible with older hardware, but it lacks the advanced mathematical tools that allow for significant bitrate reductions. At the other end of the spectrum, the high profile utilizes specific coding techniques like adaptive macro block sizes, which dramatically increase compression efficiency and reduce the overall storage footprint. However, this increased efficiency requires more CPU cycles to encode at the camera level and to decode for playback on your monitoring station. A system designer must carefully balance these performance demands because choosing a profile that is too complex for the hardware can lead to latency, dropped frames, or even system crashes during periods of heavy motion. The goal is to align the profile capabilities with the specific requirements of your hardware assets and the necessity of high-quality forensic evidence. When you configure a high-motion environment, The interaction between your GOP structure and your profile settings becomes the most significant factor in managing your total bandwidth usage. If you set a very long GOP length to save space, you are effectively decreasing the number of iframes, which drastically lowers the average bitrate, but also increases the time required for a client to start rendering a clear image. Conversely, a short GOP produces more frequent keyframes, ensuring faster stream initiation and easier seeking through archived footage at the expense of higher throughput. These parameters represent the unavoidable trade-offs that every engineer must navigate when designing a scalable network video implementation. By mastering the mathematical and architectural underpinnings of the H264 standard, you ensure that your video surveillance projects provide consistent, high-fidelity results without compromising network stability or storage longevity. See you in the next lecture. Welcome back. In this lesson, we will examine the technical mechanics of the H265 standard and how it fundamentally alters the way we compress high-resolution video streams. High-efficiency video coding, or H.265, represents a significant evolutionary step over the older H.264 standard, primarily because it addresses the growing demand for 4K and multi-megapixel surveillance footage. Achieving a 50% reduction in bitrate while maintaining visual integrity is not a result of simple optimization, but rather a deep shift in how the encoder interprets temporal and spatial redundancy. The transition from the macro block structure found in H.264 to the coding tree unit, or CTU, is the cornerstone of this efficiency. While older standards were constrained by fixed 16 by 16 pixel blocks, H.265 allows for flexible partitioning, with CTUs ranging up to 64 by 64 pixels. This adaptability is particularly useful in modern Axis camera systems, where smooth, static backgrounds can be encoded with large, efficient blocks, while complex, motion-heavy areas receive finer, more granular treatment. Effectively, the algorithm spends computational power exactly where it matters most, reducing wasted data across the resulting video file. The shift toward larger recursive block sizes introduces a sophisticated layer of spatial prediction that drastically reduces the amount of data transmitted over the wire. Within the CTU, the encoder can recursively subdivide blocks into smaller coding units, prediction units, and transform units based on the specific complexity of the scene. This nested structure allows the system to model movement or static areas with higher mathematical precision than ever before. For instance, in a large, featureless hallway, the encoder can decide to use a single large block size, whereas a doorway containing turbulent flow or complex motion is subdivided into much smaller, more descriptive segments. Because this decision-making process happens at the frame level, the system dynamically balances visual fidelity against throughput requirements. This is exactly how we maintain clarity in ultra-high resolution streams without overwhelming the limited bandwidth of an enterprise network infrastructure. However, this increased compression efficiency comes with a non-trivial computational cost that we must account for during the design phase of a surveillance project. Encoding H.265 requires significantly higher processing power because the encoder must evaluate a massive number of possible partitioning combinations before deciding on the optimal configuration for each frame. On the hardware side, this means that both the camera and the decoding client must be equipped with dedicated H.265 processing logic to avoid high latency or hardware strain. If you attempt to process these streams on older workstations lacking hardware-accelerated decoding, you will quickly observe dropped frames and a degraded user experience. Understanding these resource constraints is essential for any system designer, as you must ensure that your back-end server infrastructure is capable of handling the increased load that comes with modern, high-efficiency encoding schemes. Beyond spatial partitioning, H.265 achieves its performance gains through improved intraframe and interframe prediction models that utilize more complex motion vectors. By effectively recognizing patterns across a longer timeline, the algorithm can better identify temporary occlusion or consistent motion, leading to smaller residual data files after the prediction step. These mathematical enhancements allow Axis systems to store significantly more footage on the same physical hard drive space, which directly translates into lower total cost of ownership for the client. When you are designing a system that needs to retain video for extended periods, the choice of H.265 is often the single most impactful variable in your storage calculations. By leveraging these advanced compression techniques, you shift the bottleneck away from the network and storage layers and into the computational performance of the specialized hardware. See you in the next lesson. Welcome to this module, where we will explore AX's Zipstream technology and how it optimizes your video storage efficiency. By the end of this session, you will understand how to implement dynamic compression to manage bandwidth without sacrificing forensic detail. In this chapter, we are going to dive deep into AX's Zipstream, a proprietary compression technology designed to sit on top of standard H.264 and H.265 protocols. Many engineers mistakenly treat video compression as a purely binary choice between codec standards, but Zipstream introduces a sophisticated layer of intelligent analysis to the encoding pipeline. The primary goal is to address the fundamental trade-off in video surveillance, which is the tension between high-quality forensic evidence and the ballooning costs of storage and network throughput. Because standard codecs apply compression algorithms relatively uniformly across the entire frame, they often squander precious bits on uninteresting background data. Zipstream changes this dynamic by performing real-time analysis of the video stream to identify what actually matters to the operator or the forensic investigator. It effectively carves up the image into regions of interest and regions of static background, applying different computational priorities to each segment to achieve maximum efficiency. The engine behind this technology operates by continuously analyzing the stream to isolate areas containing motion or specific detail, like human faces, license plates, or other objects of forensic interest. During the encoding process, the system prioritizes these identified zones, maintaining the original high-resolution detail to ensure that nothing vital is lost in the compression pipeline. Simultaneously, the background elements which the camera determines are not currently of interest are subjected to a much more aggressive form of compression. This isn't a simple blurring technique, but rather a granular reduction in the bit density allocated to those static pixels. Because the human eye and computer vision algorithms are typically less sensitive to minute variations in unchanging static surfaces, this selective reduction in information allows the stream to remain highly compliant with standard VMS platforms while significantly lowering the overall bitrate. It is an application of intelligence at the edge, where the camera itself acts as the primary decision maker for data management. When we talk about the mechanics of this optimization, we must consider the control parameters available to us, specifically dynamic GOP lengths and dynamic frame rates. A traditional group of picture structure is often static, forcing a keyframe at specific intervals regardless of how much action is occurring in the field of view. Zipstream allows the camera to dynamically adjust these intervals based on the level of activity in the scene. If a scene remains completely dormant, the camera can extend the GOP length and drop the frame rate, effectively starving the encoder of unnecessary data and preventing the storage of redundant frames. This capability is critical because, in many surveillance environments, significant durations of time pass with zero meaningful activity. By configuring these dynamic parameters correctly, we can guarantee that bitrates drop to a bare minimum during these idle periods without ever risking the failure to capture a critical event if movement suddenly triggers the sensor. Achieving these results in practice requires a nuanced approach to tuning for specific scene complexities, as there is no silver bullet for every configuration. For instance, an outdoor scene with wind-tossed trees will naturally produce more noise and motion, which limits the potential efficiency gains compared to an indoor hallway. Your job as a system designer is to model the complexity of the observed environment and set the compression profile to respect those atmospheric or environmental conditions while still maintaining the integrity of the footage for third-party decoders. Since Zipstream is fully compatible with any H264 or H.265 compliant video management system, you do not need to worry about proprietary playback issues. However, if you tighten the compression settings too aggressively in a high-complexity scene, you may inadvertently introduce artifacts that obscure identification. Balancing these proprietary algorithms is not just about saving space, it is about guaranteeing that the forensic evidence remains admissible and useful when a security event eventually unfolds. We will move on to the next topic now. Welcome back. It is time that we address the critical task of accurately sizing your surveillance storage infrastructure. In this lesson, we will dissect the mathematical rigor required to guarantee that your video data remains accessible precisely as long as the law or your internal policies demand. Calculating storage requirements is not an exercise in guesswork. It is an exercise in meticulous capacity planning. We must begin by identifying our primary constants, which include the number of cameras, their individual resolution settings, and the configured frames per second. Compression efficiency stands as a variable of equal importance, as the disparity between H264 and H.265, when combined with proprietary techniques like Axis Zipstream, can alter your total storage footprint by a massive margin. Furthermore, you must account for the activity factor, which represents the percentage of time a scene contains movement that triggers high bitrate recording. If you configure a camera for continuous recording, you assume a 100% activity factor, whereas motion-triggered recording allows you to model lower usage rates to conserve disk space. Synthesizing these variables provides a raw estimate of the daily data volume in gigabytes, which then serves as the foundation for your multi-day retention requirement. Once we establish our daily storage demand, we must project this across the total retention window mandated by the client or legal authorities. A common oversight occurs when architects calculate the raw storage needs but fail to account for the overhead imposed by file system structures and RAID array parity. When you implement a RAID 5 or RAID 6 configuration to safeguard against disk failure, you must forfeit a portion of your aggregate capacity to store the necessary parity bits for data reconstruction. For example, a 3-disk RAID 5 array loses the equivalent capacity of one complete drive, which significantly impacts the effective uptime available before the system begins overwriting the oldest video files. We also need to consider the physical limits of the recording server, as the maximum write speed of the storage controllers can become a bottleneck when handling high-throughput streams from many high-resolution cameras simultaneously. Meticulous mathematical forecasting is the only way to ensure that you do not encounter catastrophic video loss before your designated retention period expires. To translate these formulas into practice, we rely heavily on specialized design tools like the Axis Site Designer to model various deployment scenarios. These tools automate the underlying arithmetic, allowing you to experiment with different compression profiles or frame rates to see their real-time impact on the required terabytes. If your initial calculation reveals that you lack the physical space for the desired retention, you have a few specific levers to pull that do not involve adding more hard drives. Lowering the resolution slightly, or refining the motion detection sensitivity can often create the necessary buffer without sacrificing the evidentiary value of the footage. Additionally, consider how archiving strategies might allow you to move older, less critical data to cheaper, long-term storage pools while keeping the most recent events on high-performance drives. Balancing these technical trade-offs requires a deep understanding of both the hardware limitations and the operational requirements of your specific network video environment. See you in the next session. Welcome back. In this module, we will explore the architectural implications and practical implementation of SD card edge storage within decentralized surveillance environments. When we design robust video surveillance systems, we often gravitate towards centralized storage solutions for their ease of management and consolidated retrieval. However, relying solely on a single point of failure within our recording servers introduces significant risk, particularly when the network infrastructure remains vulnerable to fragmentation or complete outages. Decentralized recording, specifically through the use of edge storage on the camera itself, transforms a standard surveillance device into an autonomous recording node. By utilizing an SD card inside the camera chassis, we create a failover buffer that ensures continuous video acquisition regardless of the status of the central video management system or the local area network. This architecture is fundamental to building high-availability systems where data integrity is paramount, even in the face of catastrophic link failures. It is a common mistake to assume that any piece of flash memory marketed as a high-capacity storage device will suffice for a professional security installation. We must distinguish between consumer electronics and surveillance-grade storage, the latter of which is engineered to handle the relentless write intensity of constant video streaming. Surveillance applications operate under a unique set of constraints, primarily the sheer volume of write cycles required to sustain continuous recording at varying frame rates and compression levels. A standard SD card, designed for the occasional burst of data from a digital camera, will often fail prematurely when subjected to the constant high bitrate I/O operations of an Axis network camera. We must insist upon high-endurance memory cards that are specifically validated for the thermal environments found inside an enclosed camera casing. These components utilize specialized controller logic designed to manage wear leveling across their NAND cells, effectively extending the lifespan of the storage medium in demanding, continuous write scenarios. The thermal environment within a camera housing is objectively hostile to standard flash memory. As the device operates, the heat generated by the image processor and sensor array elevates the internal temperature of the chassis, which can accelerate the degradation of non-industrial grade components. Surveillance-grade SD cards are constructed with heat-resistant materials and robust internal architectures to withstand these constant temperature fluctuations without suffering from bit rot or sudden controller failure. We must also account for the write cycle limitations inherent to flash memory, which is a finite resource governed by the physical integrity of the storage cells. By selecting cards specifically rated for high endurance, we align the hardware capabilities with the expected uptime of the surveillance system. This choice is not merely an engineering recommendation. It is a critical strategy to prevent data loss events that occur when a cheap card unexpectedly exits the recording loop due to thermal stress or hardware wear. Beyond the selection of robust hardware, we must configure our edge storage as either a primary recording target or as a smart failover mechanism. In a failover configuration, the camera intelligently detects the loss of connectivity to the video management system and redirects the stream to its local SD card. Once the connection is reestablished, the camera can automatically synchronize the locally recorded footage with the central server, effectively backfilling the timeline without operator intervention. This automated recovery process is essential for maintaining a seamless evidentiary chain throughout periods of network instability. We must also ensure that these storage partitions are properly integrated with the camera's security features, such as SD card encryption, which prevents unauthorized access to the recorded video if the hardware is physically compromised. Without these protective measures, the edge storage could become an unintended vulnerability rather than a source of system resilience. Effective health monitoring of these decentralized assets is an often overlooked aspect of system administration. Integrators should regularly query the internal status of the SD cards, which report metrics such as drive health, remaining endurance, and current recording status, to preemptively identify hardware approaching its end of life. By incorporating this telemetry into our routine maintenance, we shift from a reactive state of troubleshooting after a failed recording to a proactive lifecycle management strategy. Our goal is to maintain the reliability of the entire network by ensuring that the edge capacity serves as a transparent extension of the central storage architecture. Through careful selection of surveillance-grade media and rigorous configuration of the failover protocols, we can build a fault-tolerant system capable of surviving severe network fragmentation. These practices define the professional standard for decentralized storage, ensuring that your video data remains reliable, secure, and accessible under any conditions. I will see you in the next lecture. Welcome back to our exploration of system architecture. In this section, we examine the complexities of VMS archiving architectures, focusing on enterprise-scale data lifecycle management. Managing massive video datasets in an enterprise VMS environment requires a clear distinction between active, high-performance storage and cost-effective, long-term archival. When we design these systems, we naturally gravitate toward hierarchical storage management, or HSM, as the primary architectural pattern. The core idea is to treat storage as a tiered abstraction rather than a single, monolithic volume. Axis Camera Station implements this by orchestrating the movement of data from high-speed Tier 1 solid-state storage, where we prioritize input-output operations per second, to Tier 2 storage, such as high-capacity mechanical arrays or NAS, where cost per gigabyte is the critical optimization metric. By defining clear policies for when data transitions from the active buffer to the archive, you ensure that your most recent, high-priority footage is always available for immediate, low-latency playback. This intelligent hardware offloading preserves your primary storage bandwidth for active writing tasks, preventing the performance degradation that typically occurs when a single drive array is saturated by a mix of live recording and heavy read requests. Database management and video grooming are the operational heartbeat of a stable archiving strategy. It is not sufficient to simply move files from one disk to another. The VMS database must maintain an infallible index of every frame, regardless of its physical location on the magnetic or flash media. When we discuss grooming, we refer to the automated process of purging or archiving data when it conflicts with retention policies or storage quotas. If your system is not configured to groom old data predictably, you risk a database lockup or an ungraceful system crash when the primary storage volume reaches actual capacity. Furthermore, implementing redundant recording paths, such as dual streaming to both local edge storage and a centralized server, creates a reliable safety net against intermittent network failures. This approach mandates that you treat the file system as a transient medium, where metadata consistency remains the single most important technical requirement for ensuring that your video remains searchable and playable long after the initial recording event occurs. When we transition to the retrieval phase of this architecture, the technical requirements shift from data preservation to data integrity and chain of custody. Law enforcement and security teams often require the rapid export of forensic packages, which must be tamper-proof and verifiable. A secure archiving architecture must facilitate the export of video in a way that includes the necessary cryptographic signatures or digital watermarks to prove that the footage has not been altered since the moment of capture. This is where the physical layout of your storage hierarchy meets the functional requirements of legal admissibility. If your VMS struggles to retrieve data from a deep archive because the storage bridge is saturated, you have effectively failed the end user. You must prioritize the network throughput dedicated to export tasks to ensure that investigators can pull hours of footage without impacting the live system performance. Remember that an archived asset is only valuable if it can be surfaced, decrypted, and authenticated within the timeframes dictated by your organizational security protocol. Effective VMS archiving also demands a rigorous approach to hardware maintenance and failure recovery within the storage array itself. Spinning disks, while excellent for the capacity requirements of second-tier storage, are statistically more likely to fail than solid-state equivalents over long duty cycles. Your architecture must account for RAID parity overhead and the reconstruction time required when a member disk in a larger array needs replacing. If you do not plan for these rebuild periods, your archiving performance might drop to nearly zero during a hardware fault, causing a bottleneck in the VMS write queue. It is also vital to verify that your NAS or SAN storage protocols, whether iSCSI or NFS, are tuned to handle the sequential write patterns of high-definition video streams. By aligning the physical limitations of your storage hardware with the logical data grooming policies of the VMS, you build an ecosystem that is both scalable and operationally resilient against the high volume of incoming data. See you in the next lecture. Welcome back. In this lesson, we are establishing the foundational protocols for the physical installation of network video hardware. Let's dive straight into the professional standards required for a reliable, long-term deployment. Achieving operational integrity in a video surveillance deployment begins long before a camera is mounted to a wall. A rigorous pre-installation site survey is your first line of defense against future maintenance headaches, as it allows you to verify cable runs, lighting conditions, and potential mounting obstructions. Once on site, I strongly recommend performing a comprehensive bench test of every camera before it ever reaches its final location. This simple practice of unpacking, configuring, and verifying the device on a workbench identifies out-of-the-box hardware failures or firmware issues in a controlled environment. If a camera is dead on arrival, it is far more efficient to address it at a desk than while perched atop a 16-foot ladder. This disciplined approach eliminates the variables of site conditions, ensuring that if you encounter a problem after physical deployment, you can immediately rule out the camera hardware itself. Physical handling of electronic components requires a disciplined respect for electrostatic discharge, commonly known as ESD. Even a minor static discharge can induce latent failure points in high-density sensor arrays or processing chips, which might work perfectly during initial setup, only to fail 6 months later under thermal load. Always utilize properly grounded anti-static wrist straps when handling sensitive internal components or opening weather-sealed housings in dry environments. Furthermore, when assembly is required, pay meticulous attention to the manufacturer-specified torque settings for all housing screws and mounting bolts. Over-tightening can crack delicate composite housings or compromise the integrity of rubber gaskets, potentially allowing moisture ingress that destroys the optics. Conversely, under-tightening leaves the unit susceptible to micro-vibrations, which will eventually degrade image quality or introduce mechanical stress on PTZ motors. Choosing the correct mounting accessory for your specific surface material is not merely a matter of convenience. It is a fundamental requirement for image stability. Mounting an axis camera to soft drywall or uneven masonry without the correct backboxes or mounting plates often results in resonant vibrations that manifest as image jitter or blurred frames. For high-resolution cameras, especially those utilizing advanced stabilization features, a vibration-free fixation point is non-negotiable for achieving consistent metadata accuracy. Whether you are dealing with concrete, steel, or aluminum, verify that your fasteners are rated for the surface density and that the mounting plate provides adequate surface contact. By ensuring the physical mount is rigid and decoupled from environmental vibrations, you ensure that the software algorithms, such as motion detection or analytics, operate at their peak design performance. Executing a flawless installation serves to minimize expensive truck rolls and ensures your surveillance infrastructure remains operational over its full life cycle. Each action taken during the physical setup, from the neat dressing of network cables to the precise torquing of weather seal screws, represents an investment in system reliability. When you prioritize these foundational mechanical principles, you effectively remove the physical environment as a variable in your troubleshooting flow. If a camera stops functioning, you can confidently move to network or software diagnostic layers without needing to recheck the physical mount or suspect the cabling integrity. Mastering these protocols distinguishes a professional integrator from a casual installer, as it moves the practice from reactive troubleshooting to proactive stability. Ultimately, your goal is to build an infrastructure so physically sound that it becomes invisible to the end user by never requiring manual intervention. See you in the next lecture. Welcome back. Today we are turning our attention to the critical mechanics of mounting and sealing network cameras to ensure long-term environmental immunity. In this chapter, we will rigorously examine the procedures required to maintain IP66 and NEMA 4X ratings in the field. Achieving a truly ruggedized installation requires a disciplined approach to physical assembly that goes far beyond simply tightening a few screws. When we discuss environmental isolation, we are essentially talking about the science of preventing moisture, dust, and particulate ingress from compromising the sensitive internal optical and electronic components of the camera. The primary objective is to maintain the integrity of seals that the manufacturer has engineered to withstand extreme conditions, including torrential rain and fluctuating industrial temperatures. If a technician fails to properly seat a gasket or secure a cable gland, the resulting breach does not just risk a temporary hardware failure. It creates a point of entry for oxidation and microbial growth that will inevitably lead to catastrophic system degradation over time. You must treat every connection point as a potential pathway for element penetration that requires intentional mitigation. Relying on intuitive assembly is insufficient because the physical tolerances required to maintain these certification ratings are often narrower than what the naked eye can comfortably distinguish. Therefore, we adopt a systematic methodology that mandates strict adherence to factory specifications regarding torque, alignment, and material compatibility. By internalizing these practices, you ensure the device operates exactly as the designers intended, regardless of how hostile the installation environment becomes. One of the most frequently overlooked aspects of outdoor mounting is the management of cable entry points, specifically the relationship between the physical cable and the chassis interface. Even when high-quality proprietary cable gaskets are utilized, water has a remarkable capacity to migrate along the surface of a network cable if the proper precautions are not taken. We address this fundamental issue through the strategic implementation of drip loops, which essentially harness gravity to redirect moisture away from the camera's entry gland. A drip loop is created by forming a small, downward-facing curve in the cable path before it enters the housing, ensuring that any rainwater running down the jacket is pulled downward by gravity rather than being channeled directly into the mounting hole. Furthermore, the selection of the correct grommet for the specific diameter of your cabling is non-negotiable, as an undersized or oversized seal will inevitably fail under sustained ambient pressure. We must also consider the application of secondary environmental barriers, such as silicone sealants, which can provide an essential redundancy for legacy surfaces or uneven mounting substrates. When you are performing these tasks, the goal is always to minimize the exposure of the camera's internal chassis to the outside air, as any exchange of air introduces a risk of moisture condensation. Internal condensation represents a unique threat to electronic systems, particularly in environments characterized by high humidity and rapid temperature cycling. When a camera chassis is sealed off from the outside world, the air trapped inside during assembly retains a specific dew point, which can cause internal fogging if the temperature of the internal components drops below the dew point of the air inside the dome. To mitigate this risk, the strategic placement of desiccant packs is mandatory during the final assembly of the unit. These packs act as sacrificial moisture sponges, keeping the absolute humidity within the housing low enough to prevent condensation on the lens or interior surface of the dome cover. However, the presence of these packs does not grant us permission to be sloppy with the primary assembly of the dome cover or the tightening of seals. You must ensure that the assembly process is performed in a clean environment and that the sealing rings are seated perfectly within their grooves to prevent the introduction of new moisture-laden air. Failure to properly tighten a dome cover results in a compromised pressure differential, which renders the desiccant pack useless as it quickly becomes saturated with external moisture. Precision during this final sealing phase is the thin line between a robust, long-term surveillance solution and a maintenance nightmare awaiting the first cold front. I will see you in our next session. Welcome back. In this session, we will examine the physical layer of your video surveillance infrastructure, specifically regarding cabling and termination standards for robust deployments. When we speak of professional-grade network video systems, the cable infrastructure is effectively the backbone that supports everything else. If the data transmission fails or the power delivery becomes inconsistent, even the most sophisticated camera settings will not save your footage from being useless. We generally start with the category standards, specifically Cat5e, Cat6, and Cat6a, which define the electrical characteristics of the communication path. Cat5e is often sufficient for basic 100 megabits per second deployments, but in the context of modern high-resolution access cameras, Cat6 or Cat6a is preferred to handle the increased bandwidth and to support higher PoE current demands. Maintaining the integrity of these cables is not merely about plugging them in. It involves adhering to strict bend radius limitations. If you bend a copper cable too sharply, you change the physical geometry of the internal twisted pairs, which directly impacts packet loss and signal reflection. You must ensure that every run respects these physical limits to maintain the signal-to-noise ratio required for stable streaming. Beyond the cable choice itself, you have to be acutely aware of the environment in which you are routing these lines. Electromagnetic interference, commonly known as EMI, is a persistent threat in industrial or complex office environments where network cables run parallel to high-voltage electrical lines. If you must run your data cables near power cables, you need to ensure physical separation to prevent induced interference from causing intermittent data corruption. Even if the cable is shielded, proper grounding is required. Otherwise, the shield itself acts as an antenna for noise. For longer runs that exceed the standard 100-meter limit for copper, we transition to fiber optic systems using small form factor pluggable, or SFP modules. Fiber provides immunity to EMI and facilitates the high bandwidth requirements of multi-sensor or 4K camera arrays over long distances without the signal degradation inherent in copper. Once the cable is routed, the termination process becomes the next critical point of failure in the field. Using high-quality RJ45 connectors is non-negotiable. Cheap, poorly molded connectors often lead to mechanical failure, where the contact pins lose tension or fail to pierce the insulation of the conductor properly. In outdoor or harsh environments, simply clicking an RJ45 plug into a socket is insufficient. You should utilize specialized field termination plugs that offer ingress protection to keep moisture and dust away from the copper contacts at the camera endpoint. These connectors often include sealing gaskets or glands that, if installed correctly, create a robust environment that prevents corrosion. If you fail to terminate at the camera site with these considerations, you are effectively introducing a point of vulnerability that will eventually lead to video stuttering or complete power failure due to oxidized contact points. Reliable operation in video surveillance is fundamentally about managing variables. By adhering to these strict standards for cabling and termination, you eliminate the ambiguity that plagues unprofessional installations. Power over Ethernet requires that the resistance in your cable run be low enough to deliver regulated voltage to the camera, and inadequate terminations are a primary cause of unnecessary voltage drops. When you see intermittent network dropouts or cameras that reboot randomly, the cause is often an improperly terminated cable or an excessive bin that has fractured an internal wire. By mastering these physical layer standards, you transform your installation from a collection of parts into a reliable, enterprise-grade system. This level of detail is exactly what separates a transient hobbyist installation from a permanent network video solution. I will see you in the next lesson. Welcome to this chapter on environmental protection. In this section, we will explore the engineering requirements for deploying surveillance systems in the most hostile environments imaginable. When we shift our focus from standard indoor or benign outdoor environments to extreme locations, the hardware requirements change from mere utility to rigorous survival metrics. An access camera intended for a standard office block is not capable of maintaining structural integrity or functional operation in extreme industrial or subterranean conditions. We must evaluate the mechanical and electrical safeguards necessitated by high corrosion zones, such as marine environments, or zones where the concentration of combustible gases makes standard electrical equipment a potential ignition source. This necessitates an understanding of pressure, material science, and thermodynamic management that goes well beyond standard IP-rated housing considerations. By mastering these architectural details, you move from being a simple installer to an infrastructure engineer capable of guaranteeing uptime in the most demanding site deployments. Starting with thermal dynamics, we encountered the distinct challenge of cold start operations in sub-zero environments, specifically where PTZ mechanisms are concerned. Standard mechanical lubricants can experience increased viscosity or solidification at extreme temperatures, which places immense, potentially destructive torque strain on motor gears during an initial boot cycle. Arctic temperature control is a sophisticated methodology that integrates active heating within the camera housing to bring the internal components to a permissible operating temperature before the mechanical initialization occurs. This ensures that the physical integrity of the gears and the motors is preserved, preventing stripped gears or stalled actuators during a cold snap. The logic embedded in these cameras prioritizes the thermal equilibrium of the internal environment, effectively creating a microclimate that decouples the device's operational state from the ambient meteorological extremes. In industrial settings where corrosive elements, such as salt mist or chemical vapors, are present, stainless steel enclosures are not merely an aesthetic preference. They are a functional mandate. Standard aluminum alloys, even with high-grade powder coating, will eventually succumb to galvanic corrosion or chemical etching, leading to the breach of the internal electronic environment. The implementation of pressurized housings takes this concept further by pumping clean air or an inert gas into the enclosure, maintaining a positive internal pressure. This positive pressure physically prevents the infiltration of corrosive contaminants, dust, or moisture through any microscopic seal gaps. When you are tasked with securing environments like chemical processing plants, oil platforms, or heavy shipping ports, the selection of 316L stainless steel, combined with a positive pressure delivery system, is the only way to satisfy the long-term reliability requirements of a professional surveillance project. Hazardous areas characterized by the potential for combustible dust, fibers, or flammable gases require explosion-protected enclosures that follow international regulatory standards. The fundamental principle here is containment rather than prevention of internal sparking. These enclosures are specifically engineered to contain an internal explosion if and when it occurs. By ensuring that the housing can withstand the massive pressure wave and heat of such an event, we prevent the explosion from spreading to the surrounding atmosphere. This level of hardening requires specialized conduit seals and explosion-proof cable glands that act as flame paths, ensuring that no electric arc or hot gas escapes the controlled boundary. Engineers designing for these sites must be intimately familiar with the certification classes of their hardware, as the cost of a non-compliant deployment is measured not only in hardware destruction, but in catastrophic safety failure. Finally, we must address the management of heat dissipation and physical vibration, which interact with the enclosure dynamics in ways that are often overlooked until a failure occurs. Solar shielding is a critical design choice in high sunlight regions where excessive radiant heat on the housing exterior would otherwise cause the internal processor to throttle or the image quality to degrade due to excessive noise. Simultaneously, in transport-heavy environments like railway monitoring or machinery-dense factories, mechanical vibration can induce cyclic fatigue on mounting brackets and electronic solder joints. To combat this, we rely on high-frequency dampening mounts and rigid architectural designs that minimize the resonant frequency of the camera assembly. These mitigations represent the final tier of environmental resilience, transforming a standard network camera into a persistent node capable of providing stable situational awareness regardless of the external chaos it faces. See you in the next lecture. Welcome back. In this module, we will explore the critical, often understated discipline of managing firmware life cycles within an access network infrastructure. Firmware serves as the bedrock upon which your surveillance system's security, analytical capabilities, and hardware stability depend. Yet it is frequently treated with insufficient rigor. When you decide to upgrade a camera, you are not merely pushing a binary file to an endpoint. You are altering the behavior of a sophisticated computing device that must remain synchronized with your video management software, or VMS. This process requires a systematic approach, beginning with a disciplined review of release notes. Manufacturers document known issues, bug fixes, and security patches for a reason, and ignoring these details often leads to unexpected incompatibilities between the newer firmware and existing VMS drivers. If you apply a patch without verifying that your recording software can interpret the updated device output, you risk losing critical video data, which defeats the entire purpose of having a security system. Consequently, checking the compatibility matrix provided by the vendor is not a suggestion, but a requirement for maintaining system uptime. Once you have validated compatibility, the deployment method becomes the next focus of our strategy, especially when scaling across large enterprise environments. Managing one or two cameras is trivial, but deploying firmware to hundreds of devices requires automation via tools like Access Device Manager. This software allows administrators to execute mass updates across vast network arrays simultaneously, ensuring that all devices achieve a uniform security posture. However, mass deployment brings the inherent danger of disrupting surveillance during critical business hours. You must establish strict maintenance windows where system activity is predictable and potential downtime has minimal impact on security operations. Automating the schedule while keeping the upgrade process transparent allows you to balance the need for new features against the imperative of continuous environmental monitoring. Even with the most careful planning, the reality of network hardware is that errors can occur during the write process, which brings us to the importance of dual bank memory technology. Access devices often utilize a dual flash memory architecture, which essentially stores the current operational image alongside a backup state. If a firmware update encounters a failure, such as a power surge dropping the connection or a corrupt binary transfer, the hardware remains capable of reverting to the protected, previously functional bank. This redundancy is the primary defense against the tragedy of bricking a device, which would otherwise necessitate a manual physical recovery or a return to the factory. You must understand that this fallback mechanism is designed to prevent total system failure, but it is not a substitute for having a well-defined recovery procedure involving physical access when automatic restoration does not suffice. Beyond the technical safeguards, the ultimate goal of these protocols is to maintain a hardened attack surface against emerging threats. Security vulnerabilities are the primary driver for many firmware updates, meaning a device that is 6 months out of date is objectively less secure than one that is current. As practitioners, it is our responsibility to operationalize these updates as part of regular infrastructure hygiene rather than treating them as reactive fixes to active system failures. By automating the auditing and deployment phases and strictly adhering to validation steps, you transition from constant firefighting to proactive lifecycle management. This structure ensures that your network video architecture stays performant, secure, and ready to leverage the latest analytical features that define modern surveillance capabilities throughout the entirety of the hardware's intended lifespan. See you in the next lecture. Hello, and welcome to this deep dive into physical security hardening for your network video infrastructure. In this chapter, we focus on mitigating physical sabotage by hardening your surveillance assets against vandalism, tampering, and unauthorized access. By mastering these techniques, you ensure that your cameras remain operational even when an adversary attempts to physically compromise the system. When we talk about physical durability, the IK10 rating is the industry standard you must understand. An IK10 rating signifies that an enclosure can withstand an impact of 20 joules, which is roughly equivalent to a 5-kilogram mass dropped from 40 centimeters. This mechanical robustness is not just about the outer shell, but about how the kinetic energy of a blow is distributed across the entire mounting assembly. When you select hardware, you should always look for cast metal housings that effectively dissipate these forces away from the sensitive optical components inside. If you are installing in a high-risk area, an IK10 rated dome is not merely a recommendation, but a baseline requirement for resilience. Relying on weaker materials often leads to structural failure that permanently damages the lens focus or cracks the protective bubble during a blunt impact. Beyond the housing, the integration of specialized tamper-resistant hardware is a simple yet effective deterrent against casual interference. Using security screws that require unique bits prevents unauthorized individuals from opening the camera to adjust the lens or gain internal access to the device settings. However, hardware alone is rarely sufficient, which is why we must leverage the active sensing capabilities of modern cameras. We can use onboard accelerometers to detect any physical movement, such as an attempt to reposition the lens, knock the camera off its mount, or spray paint over the view. Modern firmware can be configured to trigger immediate notifications in your video management system the moment these sensors detect threshold deviations. This transforms the camera from a passive observer into a device that actively reports when it is being attacked. Strategic installation goes hand in hand with hardening, especially when considering the vulnerability of external cabling. If your cabling is exposed, it creates a single point of failure where a pair of wire cutters can instantaneously disconnect the device from the network. You must ensure that all cabling is routed through hardened, rigid conduit directly from the source to the mounting base. Never leave a service loop of cable exposed near the camera, as this is the primary point of attack for someone looking to pull the unit from its bracket or sever the connection. Furthermore, elevating cameras beyond the physical reach of an average person significantly complicates any attempt at direct tampering. While mounting height can be a trade-off for field of view, the security gain of placing hardware outside the hand's reach zone often outweighs the marginal loss in image detail. Designing for resilience also requires a perspective that acknowledges that every camera might eventually be compromised. One of the most effective strategies to maintain security coverage is the deployment of overlapping, redundant camera fields of view. By ensuring that one camera is monitoring the physical housing and surroundings of another, you create a system where physical sabotage is captured by a secondary, hidden, or distant observer. This creates a psychological deterrent for attackers, as they know that attempting to blind one camera only exposes them to the view of another. You should incorporate this cross-monitoring design early in the planning phase to avoid gaps in your security perimeter. This layered approach ensures that the total surveillance apparatus remains functional and accountable, even in the face of targeted, localized interference intended to induce a blind spot. See you in the next lecture. Welcome back to our technical journey through the Axis ecosystem. This chapter focuses on the configuration of Axis Camera Station, the central video management soul of your surveillance infrastructure. Configuring Axis Camera Station effectively turns a collection of scattered hardware components into a coherent, manageable video management system. You need to start by understanding the discovery process, where the software identifies devices on the network using the Axis IP utility or custom broadcast protocols. Once discovered, adding these devices requires careful attention to credentials to ensure that the initial handshake is secure and authenticated. You should always aim to organize cameras into logical device groups based on their physical deployment or functional purpose within the facility. Mapping these architectures correctly at the beginning saves significant effort when you eventually need to scale the system or manage updates across dozens of endpoints. By establishing a clear hierarchy early on, you create a foundation that supports more advanced configurations later in the deployment cycle. When addressing recording schedules, it is crucial to move beyond simple continuous recording to minimize unnecessary storage consumption. You should leverage motion triggers or physical I/O events, integrating inputs from external sensors or internal analytics to initiate recording only when relevant activity occurs. This selective recording approach is not just a storage optimization strategy. It also simplifies the task of identifying important events during forensic reviews. While configuring these schedules, ensure that your retention policies align with the business requirements or regulatory constraints inherent to the site. If you rely too heavily on basic, always-on recording, you significantly increase the risk of overwriting critical evidence sooner than intended due to limited drive capacity. Balancing trigger-based recording with a sensible, automated archiving strategy is the hallmark of a resilient surveillance system. Managing access through user roles represents another critical layer of system security that administrators often neglect during initial setup. AX's camera station allows for deep integration with Active Directory, which is a best practice for enterprise environments where manual account management leads to security gaps. You should define roles that adhere to the principle of least privilege, providing users with only the specific permissions required for their operational tasks. For instance, a security guard needs access to live monitoring and forensic export, but they rarely require the ability to modify system event rules or network settings. By implementing strict audit trails that log every user interaction, you can maintain accountability and verify the integrity of the system during routine security reviews. This centralized permission management transforms the VMS into a well-governed platform rather than an open door for unauthorized activity. Finally, you must master the event rules and smart search capabilities to maximize the operational return on your configuration efforts. Event rules act as the logic engine of the system, allowing you to link analytic triggers, like line crossing or object detection, to automated responses such as PTZ presets, email notifications, or internal I/O port toggles. When you configure these rules, avoid creating overly sensitive thresholds that lead to alert fatigue, as this will result in operators ignoring critical data over time. Smart search functions complete the workflow by allowing you to quickly filter massive amounts of recorded data based on specific metadata or motion zones, which drastically reduces the time spent on post-incident forensic investigations. When you successfully synchronize your forensic requirements with the capabilities of the Smart Search tools, you enable your team to react with precision during sensitive events. See you in the next lecture. Welcome to the chapter on securing your surveillance infrastructure. We will systematically analyze the technical requirements for hardening access devices against modern network threats. Cybersecurity in a modern network video system is not an optional configuration, but a foundational pillar of design that must be treated with the same rigor as image quality or storage retention. When we talk about hardening, we are effectively discussing the process of minimizing the attack surface by eliminating unnecessary entry points and strengthening those that must remain. A device left with factory default configurations is essentially an unmanaged endpoint waiting for an exploit, regardless of how sophisticated the hardware itself might be. We start by addressing the identity of the device within the network, specifically through the implementation of IEEE 802.1x port-based network access control. By requiring authentication before a camera can even communicate with the local network switch, you prevent unauthorized physical intrusion or spoofing at the hardware level. This protocol relies on a radius server to verify credentials, ensuring that only trusted physical connections result in active network access. As technicians, we should view this as the first line of defense to keep the surveillance network isolated from the broader enterprise environment. Once the physical connection is secured, our focus must shift to the data in transit, where HTTPS encryption serves as the primary mechanism for preventing eavesdropping. Relying on plain HTTP for camera management or video streaming is a critical vulnerability, as it allows attackers to sniff credentials or intercept sensitive surveillance footage over the wire. We achieve effective encryption by managing signed certificates, which verify the identity of the camera and establish a secure, encrypted tunnel between the client and the device. This process necessitates a clean PKI, or public key infrastructure, to handle certificate requests and validation effectively within your domain. Without a robust certificate strategy, you might find yourself troubleshooting browser-level warnings that encourage users to bypass security altogether, which defeats the entire purpose of encryption. Always aim to replace self-signed defaults with corporate trusted certificates to ensure that the entire trust chain remains unbroken. We must also audit the device services, as every enabled port on a camera is a potential door that could be left unlocked. A common hardening oversight is keeping legacy protocols running, like HTTP or Telnet, which transmit sensitive information in clear text. Disabling unused services such as FTP, UPnP, or unnecessary discovery protocols reduces the number of reachable services that an attacker might probe for vulnerabilities. Furthermore, enforcing strong, complex password policies is a non-negotiable requirement for any hardened device. We must move away from shared credentials and instead ensure that individual local accounts are managed with sufficient password entropy to thwart brute force attempts. It is equally important to manage IP address accessibility, perhaps by using access control lists, to ensure that management interfaces are only accessible from designated administrator workstations rather than the entire network. Finally, we need to consider the risks introduced by auxiliary features like external dynamic DNS, which can unintentionally punch holes in your network security posture if left unmonitored. While dynamic DNS is convenient for remote access, it often bypasses the primary firewall, potentially exposing the camera interface directly to the open internet. If remote access is required, the best practice is to leverage a secure VPN or an authenticated gateway, rather than exposing internal devices directly. When you combine these rigorous configuration standards, you create a hardened system that is significantly more resilient against automated exploits and malicious actors. By standardizing these hardening protocols across your entire fleet, you ensure that the surveillance data stays confidential and that the video system remains a structurally isolated component of your network. Consistency in these configurations across your deployment is what separates a secure, professional-grade security infrastructure from one defined by accidental vulnerabilities. Catch you in the next lecture. Welcome back, and let us now turn our attention to the operational capabilities of Axis Device Manager for enterprise-scale fleet maintenance. This chapter provides a focused look at how to streamline your administrative workflows across complex, multi-site installations. Managing a handful of network devices is a task that barely requires specialized software, but moving from a dozen cameras to a fleet of hundreds changes the requirement entirely. When you operate at scale, individual device configuration becomes a liability rather than a mere manual task. The Axis Device Manager application is designed specifically to mitigate this complexity by providing a centralized command center for mass configuration. By using this tool, you shift your methodology from per-device interaction to template-based management. This transition is essential for maintaining baseline consistency across various geographic locations, ensuring that your security policies, network configurations, and device settings remain uniform. Without such tools, the risk of configuration drift, where minor, undocumented changes accumulate over time, becomes a significant operational threat. The primary utility of Axis Device Manager lies in its automated discovery mechanism, which identifies and polls all supported Axis devices on your network segments. Once the devices are identified, you can aggregate them into logical groups, which serves as the foundation for bulk administrative actions. Whether you need to update firmware across a dozen distinct sites or push a revised set of cybersecurity protocols to your entire fleet, the management interface allows you to execute these tasks as a single atomic operation. This approach effectively eliminates the human error associated with repetitive data entry, as templates ensure that every camera receives the exact same parameters every time. Furthermore, the ability to reconfigure IP addresses or reset authentication credentials for an entire fleet at once significantly reduces the labor hours typically spent on routine lifecycle maintenance. Beyond configuration management, the tool plays a vital role in proactive system health monitoring, which is critical for maintaining maximum uptime in complex deployments. You can visualize the status of your entire fleet at a glance, instantly identifying devices that are offline, suffering from connection degradation, or nearing the end of their operational lifecycle. This proactive stance is supported by integrated warranty tracking, which allows administrators to manage their hardware assets with foresight rather than reacting to failures after they have impacted security operations. If a device stops responding to heartbeats, the system logs the incident, allowing you to prioritize your maintenance trips based on actual system intelligence. By integrating these lifecycle tracking features into your daily management routine, you move away from a reactive posture and toward a stable, Manageable network environment. Cybersecurity remains a persistent concern in modern video surveillance, and the management of secure communication certificates is one of the most tedious manual tasks for a systems administrator. Axis Device Manager simplifies this by acting as a deployment engine for digital certificates, allowing you to automate the distribution of trust across your entire infrastructure. You can enforce policies that require encrypted HTTPS connections or specific identification protocols, ensuring that your systems comply with organizational security requirements by default. By defining these policies within the management tool, you ensure that even newly installed cameras inherit the correct posture the moment they are provisioned on the network. This standardization is not merely about convenience. It is a fundamental pillar of maintaining a hardened network environment where every device acts as a secure node. Developing a disciplined workflow around device management is an investment in the long-term reliability of your video infrastructure. As you integrate these tools, remember that the objective is to create a set of repeatable, automated processes that remove the need for manual intervention whenever possible. Start by auditing your current manual tasks to identify the most common configuration changes, as these are excellent candidates for transition into standardized templates. Once you have documented these processes, implementing them within the management suite will drastically improve your operational efficiency and minimize the potential for configuration errors. While the initial setup of your device management strategy requires careful planning and testing, the result is a massive reduction in the ongoing administration effort. Your focus should remain on using the tool to enforce consistency, monitor system health, and secure your network assets effectively. See you in the next lecture. Welcome back. This lesson focuses on the systematic methodology required to troubleshoot and resolve hardware faults within an Axis network video system. When we address hardware failures, our primary goal is to minimize system downtime by isolating the fault with clinical precision. We must move away from guesswork and adopt a structured diagnostic process that systematically clears potential failure points one by one. Start by examining the camera diagnostic logs, as these files often contain the most reliable indicators of internal health, such as unanticipated reboots or component state changes. If the logs are silent, move your attention to the power over Ethernet budget, as PoE anomalies are a frequent source of intermittent hardware instability. You should monitor the power draw metrics on your switch port to ensure the device is not entering a brownout state during high-load operations, such as when IR illuminators activate or PTZ motors engage. If the power supply is stable, the next logical step involves evaluating thermal sensor alerts displayed within the management interface. An overheated processor or sensor can trigger a shutdown, so verifying environmental conditions is essential before you consider a physical component replacement. Failures in electromechanical units, specifically pan-tilt zoom systems, demand a slightly different diagnostic focus. These devices suffer from mechanical wear, which often manifests as grinding noises or a loss of positional accuracy during calibration cycles. If a PTZ camera fails to complete its startup homing process, the issue might be an obstructed movement path or internal belt degradation. Deep mechanical understanding is required here, as you must distinguish between a software-defined movement constraint and a physical failure of the stepper motors or gearing. Similarly, focus-related errors often point to a degrading motor assembly or an issue with the back focus adjustment mechanism. When you encounter these electromechanical symptoms, avoid jumping straight to a full board replacement. Instead, inspect for physical debris or obstructions that might prevent the motor from reaching its target position. By treating the PTZ mechanism as a physical machine with expected mechanical tolerances, you can better identify when a component has simply exceeded its operational lifespan. Once you have ruled out mechanical and environmental factors, we must address the integrity of the data storage and transmission path. Corruption on an onboard SD card is a classic scenario that can lead to system instability, especially if the device attempts to write logs or footage to a damaged sector. You should prioritize running a file system check or performing a card swap to determine if the storage medium is the primary bottleneck. If the storage is not the culprit, perform a physical loopback test with a known good patch cable to isolate whether the Ethernet port or the cabling infrastructure is the point of failure. This technique eliminates environmental damage to the cabling as a variable and allows you to confirm that the camera's internal network controller is working as expected. If the camera remains unresponsive, even through a direct, short-run patch cable connection, conducting a factory default reset is the final software-based hurdle to clear. A hard reset brings the device back to its baseline firmware state, effectively stripping away potential configuration-based conflicts that might mimic a dead hardware state. The cumulative effect of these diagnostic steps is a drastic reduction in your mean time to repair, which is the most critical metric for any security professional. Replacing parts prematurely is not only expensive, but is also a symptom of a weak diagnostic process that lacks the rigor required for enterprise-grade infrastructure. When you follow this isolation chain, checking logs, verifying power, assessing mechanics, testing storage, and clearing configuration, the resulting conclusion regarding the hardware status is rooted in empirical data. This evidence-based approach is what allows you to confidently categorize a fault as a terminal physical failure rather than a manageable firmware or network issue. By adopting this mindset, you ensure that every technician in the field is using a standard language for defect reporting, which is invaluable for long-term inventory planning and vendor communication. The reliability of your critical security assets relies on this discipline, ensuring that you can restore vital surveillance capabilities with the efficiency that mission-critical systems demand. See you in the next lecture. Welcome back. In this chapter, we will address the critical challenge of resolving network latency and throughput bottlenecks to ensure the seamless delivery of high-resolution video. When we talk about latency in the context of network video, we are primarily concerned with the time it takes for a data packet to travel from the camera to the recording server or viewing client. Video streams rely heavily on predictable arrival times, and when that predictability disappears, we observe stuttering or dropped frames. Packet loss is often the most significant contributor to this degradation, as the H264 rendering process is highly sensitive to missing data. If a packet is lost, the decoder cannot complete the frame interpolation, which often leads to visible artifacts or a complete freeze in the image. Furthermore, jitter, which is the variance in the delay of received packets, forces the video buffer to work harder to reassemble the stream in the correct order. This reassembly process consumes computational resources and increases the overall latency of the entire surveillance stack. To diagnose these issues, one must look deep into the network layers, specifically at the behavior of TCP and UDP protocols. While modern video streams often utilize UDP for real-time delivery to avoid the overhead of retransmissions, the underlying infrastructure still relies on TCP for management and configuration traffic. Delayed TCP acknowledgements can inadvertently throttle the throughput of the entire stream if the network stack perceives the delay as congestion. When analyzing complex topologies, you should leverage packet sniffing tools such as Wireshark to dissect RTP streams. By inspecting the sequence numbers of packets, you can determine exactly where the loss is occurring. If you observe gaps in sequence numbers that correlate with periodic stuttering, you are likely looking at a physical layer issue or a misconfigured network device that is dropping traffic. Layer 2 and Layer 3 misconfigurations remain frequent culprits in enterprise surveillance deployments. Specifically, spanning tree loops can create broadcast storms that temporarily saturate switch ports, leading to massive spikes in latency and packet loss. Similarly, if your environment utilizes multicast for video distribution, understanding the nuances of IGMP snooping is vital. Without proper configuration, multicast traffic may be flooded to every port on a switch, overwhelming end devices and causing the very latency you are trying to mitigate. You should also investigate your quality of service tagging policies to ensure that video traffic is appropriately prioritized over lower criticality data. When a switch receives more traffic than its uplink can handle, it will prioritize egress based on these tags, effectively protecting your video streams during periods of high network activity. Bandwidth saturation is a physical reality that we must acknowledge when dealing with high-bandwidth cameras. If you examine the switch port statistics, look specifically for counters related to dropped packets or CRC errors. A CRC error often indicates a faulty cable or physical interference, while a high number of dropped packets typically suggests that a buffer on the switch is overflowing. This overflow happens because the ingress data rate exceeds the egress capability of the switch uplink. To fix this, you may need to reconsider your switch topology, perhaps by moving to a design with higher capacity uplinks, or by segmenting the network into smaller, more manageable VLANs. By systematically analyzing the port statistics for every switch in the path, you can isolate the bottleneck and restore the stability of your high-resolution streams. Optimization is not just about raw throughput. It is about the reliability of the entire data pipeline. Once you have identified a bottleneck, you have the opportunity to adjust frame rates or bit rates to fit the available bandwidth while maintaining essential situational awareness. Remember that a smooth, lower resolution stream is almost always preferable to an intermittent, high resolution feed that constantly loses frames. Technicians who master these diagnostics become the guardians of real-time monitoring and ensure that security operations can function without the constant distraction of technical failure. Your goal is to create a deterministic flow where latency is kept to a minimum and packet loss is eradicated. Through careful monitoring and disciplined configuration, the complexities of even the most intricate network topologies become manageable. Study these concepts carefully to ensure your networks remain performant and stable. We'll see you in the next section. Hello, and welcome back. In this session, we will examine the technical nuances of correcting image quality anomalies to ensure your surveillance network maintains forensic integrity. We will move beyond basic settings to address complex optical and photometric issues that often plague deployed camera systems. When you encounter severe image degradation, the first step is always to isolate whether the issue is purely optical or electronic. If a feed appears constantly out of focus or exhibits hunting behavior, suspect the PTZ mechanism or an accumulation of debris on the outer dome. Cleaning an optical dome might seem trivial, but using improper materials can introduce microscopic scratches that cause light scattering, which mimics the effect of fog or blur. Once you ensure the glass is pristine, examine the PTZ calibration status through the camera interface. If the aperture is not correctly communicating with the controller, it will fail to adjust for varying light levels, resulting in constant overexposure or underexposure. Motion blur is another frequent complaint, often stemming from an incorrect balance between shutter speed and scene illumination. In scenarios where the gain threshold is set too high, the camera attempts to amplify the signal in low light, which inevitably introduces chromatic noise and reduces the overall temporal resolution of the video. You should manually override the exposure settings to prioritize a faster shutter speed if capturing fast-moving subjects is the primary operational requirement. While this necessarily increases sensor gain, it allows for a cleaner extraction of forensic details compared to a blurry image. Always verify that your WDR settings are not inducing ghosting artifacts, as these are often caused by the camera failing to align the short and long exposure frames effectively in high-contrast environments. IR reflection is a common headache for installers, particularly when cameras are mounted near walls, soffits, or reflective surfaces. When the integrated infrared illuminator hits a nearby object, it scatters back into the lens, creating a localized flare that washes out the rest of the scene. The solution here is often mechanical, realigning the camera, or utilizing an external infrared illuminator that does not share the same optical path as the lens is the most effective approach. If relocation is not possible, you must adjust the infrared power levels or mask the specific areas in the frame where the reflection occurs. This granular control over the illumination profile prevents the sensor from being tricked into thinking the entire scene is bright, which otherwise leads to the rest of the surveillance area appearing unnaturally dark. Addressing severe backlighting washouts requires a disciplined look at the exposure zones and dynamic range parameters. If a scene contains a bright window behind a subject, the default exposure algorithm often defaults to the brighter light source, rendering the subject as a silhouette. By defining specific metering areas, you can force the camera to ignore the intensity of the window and accurately expose the foreground pixels. Remember that every adjustment within the photometric pipeline represents a trade-off between contrast, detail, and noise levels. Systematic analysis involves looking at the raw signal before and after applying noise reduction algorithms, observing how the camera handles transitions between high-gain and low-gain states. Maintaining these systems is less about constant tweaking and more about establishing a baseline for expected performance. When an anomaly arises, compare the current behavior against the known optical limitations of the specific sensor type you have deployed. By documenting these anomalies and your mitigation steps, You create a standard operating procedure that helps reduce troubleshooting time during future service visits. Mastering these diagnostics allows you to move from passive operation to an active state of network health management. This approach ultimately ensures that the surveillance footage remains useful for its intended purpose, even under challenging environmental circumstances. See you in the next session. Welcome to our final session, where we will perform a comprehensive synthesis of the core technical domains required for the AXIS AX0-100 certification exam. In this concluding review, we will integrate the diverse concepts we have studied to ensure you are fully prepared for the challenges of enterprise network video design. When approaching system design, the intersection of pixel density and lens focal length remains the fundamental starting point for any successful deployment. We have learned that the DORI standard, covering detection, observation, recognition, and identification, provides the necessary metrics to ensure that design expectations align with physical camera placement realities. You must recall that field of view mathematics are not abstract. They are the constraints that dictate whether a scene provides actionable data or merely low-resolution noise. When calculating required sensor resolution, always verify that your pixel density per meter meets the specific operational requirement determined by the client's security goals. By anchoring every project in these mathematical bounds, you transition from arbitrary camera positioning to a defensible, engineered solution that satisfies the rigorous requirements of a professional video environment. In the domain of camera technology, understanding sensor dynamics and optical control is equivalent to knowing the raw capabilities of your primary data acquisition tools. We have analyzed how aperture, iris control, and focal lens types influence the incoming light before it is even processed by the ISP. Features such as wide dynamic range and Lightfinder are not just marketing terms. They represent sophisticated photometric algorithms designed to maintain image utility under extreme lighting imbalances. Whether you are dealing with high-contrast backlit scenarios or near-total darkness, the goal is to interpret these conditions through the lens of technical limitation and software-mediated correction. Remember that thermal imaging, while distinct, follows its own set of physics that bypasses traditional optical constraints to provide visibility where visible light sensors inevitably fail. The network and compression layers represent the conduits through which your data becomes usable system information. And here, bandwidth management is paramount. We have explored the nuances of PoE standards, confirming that power budgeting must always account for total draw, including IR illuminators and motorized PTZ components. Regarding H.264 and H.265 compression, you should reinforce your understanding of how interframe predictive coding and AXIS Zipstream technology drastically reduce storage footprints without sacrificing legitimate forensic detail. Addressing multicast versus unicast traffic is another critical inflection point. Improper configuration here often leads to network congestion that can compromise an entire security infrastructure. A robust system requires you to treat network configuration, IP addressing, and multicast scoping as inseparable components of the final video stream delivery chain. Hardware installation and cybersecurity hardening form the protective shell that maintains the integrity of the data you have worked so hard to acquire. Proper mounting and cabling techniques are easy to dismiss as mechanical tasks, yet they are the primary defenses against environmental ingress and physical sabotage. Firmware management and device security through AXIS Device Manager are not suggestions. They are the baseline requirements for modern, hardened enterprise environments. When a field issue arises, the ability to methodically isolate faults, distinguishing between network latency, storage bottlenecks, or sensor degradation, is what separates a technician from a true systems engineer. This holistic mindset, which integrates everything from the physical mount to the cybersecurity policy, is precisely what the certification exam probes to ensure you are ready for the field. Good luck with your exam preparations. I will see you on the other side once you have completed your certification.